wants to discuss. I'll try to keep everyone on schedule. So when you have 3 minutes left, so you've gone 12 minutes, I'll just jump on and give you a reminder. And if you could just wrap up so that we have time for questions, that would be extremely helpful. So we'll do the same thing we did yesterday, just share your screen to do your presentations. And Nick and I can also help with the questions in the chat. So our first speaker is Catherine Wilka from MIT, going to talk about SD-WACCM's DNOI parameterization.
Thank you so much. Hello, good morning, everyone. Let me share my screen. Are people seeing the presenter view or the view I'm trying to share? Yeah, I thought so. Let me swap displays there.
Okay,
that should be better.
Yes, that's good.
Excellent. All right, get back to the beginning. Okay. First, I'd like to thank my collaborators, my advisor, Susan Solomon, Doug Kennison, and David Tarasek. I'm a graduate student at MIT, and I'll be talking today about updating SD-WACCM's DNOI parameterization and specifically how to improve the simulation of Arctic ozone loss under extreme conditions. So as I think most of us here know, the Arctic spring of 2020 was a very extreme year for ozone loss. This was mainly due to a very cold, stable polar vortex, which allowed the formation of more PSCs than is usual in the Arctic, and allowed that to persist into the spring. And this has been reported by a number of people already, and I know there's several other papers currently about to come out about it. It was just a very, very cool year, and we wanted to look at it both in the model and also see what would happen if we pushed the model to something even more extreme, which was the motivation for simulating both the real world using the 2-degree model nudged to mirror 2's meteorological fields, as known as the specified dynamics version of WACCM. And also we wanted to see what would happen under what's called a world avoided scenario where the Montreal Protocol was never passed. So in that one, which is a much more extreme chemical scenario, we just assumed that anthropogenic ozone depleting substances would have been uniformly increased at 3.5% per year from 1985 onwards, which is about the slope of the trajectory they were on before they began to decrease. And we wanted to see how well the model could capture the real world and what it thinks would have happened in this already extreme year had we had even more chlorine in the stratosphere. So the first thing that we ran into was some problems with representing the real world. And some of those problems we managed to trace back to the denitrification scheme, which is the main subject of my talk today. So initially, we saw that our ozone profiles and our total column ozone depletions were not matching observations as time went on in the spring. They started off pretty good, as you can see by this initial profile compared to in green sonding taking at Eureka Station back in January. But by the time you get to March, or end of March, you can see that the reference run or the real world run, which is shown in blue, is really not depleting nearly as much as the station sond in green. And that gives us obviously less confidence in what is being predicted for this hypothetical world avoided. So we started looking into this, and one of the main things that jumped out was denitrification. So as a quick overview, reactive nitrogen will bond with chlorine and convert the active chlorine that destroys ozone back to reservoir form, which short circuits the catalytic ozone depletion cycles. So if instead the nitric acid sediments out of the stratosphere, however, that nitrogen is no longer present to react with chlorine, and instead those catalytic cycles will just keep destroying ozone. So we looked at MLS, and where noted that WACCM wasn't denitrifying enough, especially early on compared to MLS, and it therefore recovered faster in the model than in the observations, and essentially you did not see this, the nitrogen levels driven low enough here. So this is MLS data down below, and this is what was our original reference run up top. And while the MLS daily data obviously doesn't have complete coverage, it's good enough to see that you just have these very high levels of nitric acid in the model that you really don't pick up in the observations, and also that the observations seem to show a much broader extent of deep denitrification in the center of the vortex. So what we then did was run multiple versions of our reference runs with different NAT particle densities to drive denitrification harder, increasing it by a factor of or 5 or 10 each time. And so this was our initial one, and this is the final one. And this is, if you compare back, the same plot from before, but for the most extreme denitrified version. And again, the spatial coverage when matching MLS is a little sparse, but you can see that the center here, region here, is a much better match in spatial extent, and it also looks like we're getting these levels around sort of 7, 8 ppBV rather than getting the ones up around like 11 and 12 that we were before. So this HNO3 levels look better. And then when we compared to the ozone profiles, which are shown in the lower plot, the new ones now, those also now looked a lot better. So I just want to note that our final choice of NAT particle density parameter was chosen due to the fact that it gave a slightly better prediction of the ozone profile. It's the purple line here. However, all of the 3 most denitrifying runs are significant improvements over the blue line up here. And the effect clearly does begin to saturate a bit. But we ended up choosing what's here, this reference 008, which is shown in purple. So armed now with our better denitrification, we compared total column ozone against the OMI satellite. So we think that this is a pretty good match. We don't find any large contiguous areas below 220 Dobson units in WACCM, which is the traditional measure for kind of an ozone hole in the Antarctic. There are a few small spots below that amount in OMI, but OMI here is a 1/4 degree resolution as opposed to WACCM's 2-degree resolution. And there's only a couple small isolated spots, which also is consistent with what other groups have reported, that there might have been a few days where you had several points below that level, but you never had kind of a true ozone hole by the 220 Dobson unit definition. However, had we lived in a world where Montreal Protocol was not enacted, or where it was not followed or didn't work for some reason, the situation would have been very different. So according to SD-WACCM, in 2020, in the world voided, we would have seen, with the caveat, of course, that this is still standard specified dynamics, and so we're not capturing feedbacks onto the meteorology. But given that caveat, we would have seen an ozone hole of nearly 20 million kilometers squared, which is quite respectable even by Antarctic ozone hole sizes. And significantly, this area, which is getting down below 200 and sometimes even below 150 Dobson units, would have stretched across the pole itself and also over a lot of fairly populated areas in Canada and Alaska, and also parts of Russia and Greenland. So we think that this is a very nice result and a very nice example of how the model can be used to look at extreme hypothetical cases. Just to show this in another way, if we look at the minimum Arctic ozone in both the real world and the world avoided, we again see, first of all, see a good match with OMI observations over the entire time period from 2010 to 2020, which is what's shown in the small teal dots, and OMI is shown in the dark blue dots. And we see that in 2020, we would have had, rather than our normal spring maximum in ozone, you would have seen this sort of dipper shape that's so characteristic of Antarctic polar cap minimum total column ozone. And then just going back to the vertical profiles quickly, we once again, we see a shift towards near total depletion in the model in broad regions of the lower stratosphere rather than just at like a couple levels. When we look in the Antarctic to see what it's doing there, it's already pretty saturated in the lower stratosphere. You don't have much ozone left to destroy anyways, so most of your changes are showing in gas phase effects higher up. So then the next steps in looking at this change to the model is figuring out the impacts elsewhere, because we are obviously focused on the Arctic and specifically the 2020 Arctic, but we want to make sure that this didn't break the model in any respect that we didn't want elsewhere. So if we start by looking at the Antarctic, so some preliminary work by my colleague Brian has shown that we don't seem to be denitrifying too much. With looking at some comparisons with MePass distributions, seems to say that our reference state has improved, but again, this is pretty early work and more work's needed. One thing we need to do is to do some more careful comparisons with observations to decide on what our final nitric acid trihydrate parameter value should be. So before I mentioned that we chose among sort of the three most extreme denitrifying runs, we chose the one that made the ozone match the best. And that was partially because the MLS daily HNO3 resolution is just not, the coverage is not quite good enough to really distinguish between, these are two of the most extreme, the third most extreme and the most extreme case. So we'll need to look at some more detailed observations in order to really see what the difference in nitric acid is itself in the data and which is more justified. But we're confident that increasing the denitrification of WACCM allowed the model to more accurately simulate these conditions of the meteorologically extreme Arctic spring. And this then translates into having more confidence in its ability to simulate a world avoided, which the real world averted through the Montreal Protocol. And so far, this does not appear to degrade the representation of HNO3 elsewhere, but quantification of that is ongoing. Thank you.
Okay, thank you, Catherine. We have a question from Simone in the chat. I don't know if it's easier for you to read the chat questions, possibly.
Sure. I just wondered what the difference was actually before the fix. What column ozone did you get? What's the difference between, in the column? You showed the
yeah, so I don't remember that off the top of my head. I know that we were not getting deep enough in total column either. That was part of the thing, and it kind of marched steadily downwards as we denitrified more. And again, you saw the saturation effect where the change from between our initial reference run and like the middle denitrification levels was pretty severe. I want to say on the order of 10 Dobson units, but I don't have that off the top of my head.
Yeah, and certainly after you tested it, you would recommend getting it into the model. So future simulations would use the correct denitrification and fix, basically. Okay, great. Thank you.
Okay, if there's no more questions, let's move on so we can stay on schedule. Thank you, Catherine. Next up is Fernando Iglesias Suarez from DLR, who's going to talk to us about tropical stratospheric circulation and ozone coupled to Pacific multi-decadal variability.
Now, can you hear me?
Yes.
Cool. Cool. Hi, everyone, and thanks for having me here, giving me the opportunity to present our latest work on tropical stratospheric circulation and ozone coupled to the Pacific at multi-decadal time scales. Circulation of air in the stratosphere is largely controlled by the Brett-Dobson circulation, which is characterized by rising motion in the tropics, forward flow in the stratosphere, and sinking at mid and high latitudes. It's also considered to consist in two branches: the shallow branch, controlling the subtropical lower stratosphere all year round, and the deep branch effective in the winter hemisphere. And we are interested in understanding how the Brett-Dobson circulation may change in response to climate change, because among other things, it modulates ozone in the stratosphere, but also in the troposphere via stratosphere-troposphere mass exchange. And one of the most robust features in climate models projections due to climate change is the acceleration of the Brett-Dobson circulation. Also, we have, let's see if I can, Also, we have observational reanalysis based evidence of this acceleration in the recent past, particularly in the lower stratosphere or the shallow branch, but we have more limited evidence in the middle and upper stratosphere, maybe associated with large interannual variability, but also due to relatively short periods. And this is the region we are most interested in this work, the tropical middle stratosphere, not only for circulation, but also for ozone. And in despite of the first signs of global stratospheric ozone recovery, ozone in the tropical middle stratosphere has been declining since the 90s and remained relatively low in the last decade or so. And although long-lived halogens deplete stratospheric ozone globally, this region, ozone is most sensitive to nitrogen chemistry, which also is very sensitive to changes in transport or the Brett-Dobson circulation. So in addition to year-to-year variability, there are other modes of natural variability, particularly noteworthy for our purpose, the stratosphere-troposphere coupling, may be the decadal variability in the Pacific Ocean, as its impact has been felt globally. So for example, strong warming in global mean surface temperature has been linked to the positive phase, and warming hiatuses to the negative phase of this decadal variability in the Pacific Ocean. And this decadal variability can be diagnosed in different ways. In our work, we use the interdecadal Pacific oscillation, and is characterized by warming in the tropical Pacific during the positive phases, and cooling or relatively cold waters in the tropical Pacific during the negative phases. So in our work, we want to explore, or we explore, the mechanism that may explain a connection between low frequency variability in the Pacific Ocean with the strength in the Brett Dobson circulation and the resulting knock-on impact in ozone levels in the tropical middle stratosphere. To do that, we use CSM with WACCM, that includes interactive chemistry in the stratosphere and the troposphere, coupled to the radiation scheme. We used two main simulations, one to understand, to explore internally generated variability, a pre-industrial control run that was forced just with a pre-industrial boundary conditions, with non-evolving boundary conditions. And the model calculates its own variability, including sea surface temperature and sea ice. And to explore the role of different forces during the recent past, we used a simulation that was run driven by observed forces, both anthropogenic and natural, and also sea surface temperature and sea ice were imposed. Also, we use ozone observations from the SWOSH database that merges different satellites and provide a gap-free zonal mean ozone fields. Observations from sea surface temperature are taken from the NOAA dataset. And as I mentioned, there are different ways of calculating the IPO index. And for this, we use the triple index described in Benjamin et al., which is rather simple. It's just a residual of the deseasonalized sea surface temperature in the tropical Pacific after subtracting the sea surface temperature average over region 1 and 3. And then a low-pass filter is applied, which is coherent with the maximum local variance. So first, we started exploring low-frequency variability in stratospheric ozone linked to the Pacific Ocean. And the figure shows a cross-section, altitude, latitude, where we regressed the zonal mean ozone to the IPO index, revealing this signal peaking in the tropical middle stratosphere. And this IPO fingerprint was also simulated in the recent past, and the whole fingerprint is in good agreement with observations. Mention again that ozone in this region is most sensitive to nitrogen chemistry, and this chemistry is also sensitive to relative changes in transport time scale and the Brett Dobson circulation, and this is what we want to explore. So now we explore a potential mechanism that couples these dynamical and chemical processes to link ozone and the Pacific Ocean in the tropical middle stratosphere. So these figures show a time series of low-pass filter standardized anomaly of the IPO and the various fields that explain this mechanism in the tropical middle stratosphere for both the pre-industrial run and the real world, if you like, run. So also mention that in our work, we diagnosed the Brett Dobson circulation as the advective vertical component of the transformed Eulerian mean. And we can see how this low frequency variability in the Brett Dobson circulation in orange is linked to the Pacific Ocean in red in both simulations. And also how this low frequency variability in the Brett Dobson circulation affect ozone via nitrogen chemistry. And this is because relative changes in the transport time scale affect the breakdown of nitrous oxide into more reactive species. So overall, this show or support following previous studies that a dynamical, which is the Brett Dobson circulation process with chemistry, the nitrogen chemical processing, to explain this IPO ozone link in the tropical middle stratosphere. So briefly, a positive phase of the IPO, those relatively warm waters in the tropical Pacific are associated with a relatively rapid Brett Dobson circulation that reduce the breakdown of nitrous oxide into the more reactive species and therefore slowing down ozone loss rate, which results in greater ozone levels. And the opposite is true for the negative phase of the IPO. So then we will explore a potential impact of this IPO-like variability in recent trends in the Brett Dobson circulation. These figures showed the annual mean time series of the breadth of sun circulation within the tropics for both the deep branch and the shallow branch from 1979 to 2010. And we chose this period because it encapsulates a shift of the IPO phase between the positive to a negative phase around year 2000. But it also is where the most observational and reanalysis-based studies are focused on. And you can see how our simulations are in good agreement with previous studies, where we simulate an acceleration of the breadth of sun circulation in the shallow branch, but a non-significant change in the deep branch, which is the region we are most interested in. But it's after we take into account the IPO-like variability, and that is via removing the linearly congruent signal of the IPO from the breadth of sun circulation, that we can focus on the residual long-term trend in the breadth of sun circulation that may be more associated with climate change and stratospheric ozone depletion. And now we can see how we have steeper and positive trends in both the deep and the shallow branch between 10 and 15%. Now, because different observational and reanalysis-based studies focus on different, slightly different periods, and they show somehow more inconclusive results for the deep branch, we wanted to test the robustness of these structural changes by looking into shorter periods and also looking into different endpoints of the trend. And we did that by calculating the trends in successive 20-year periods, ending up having 12 individual trends or composite. And again, we can see that is after taking into account the IPO-like variability, where we have these steeper and positive significant trends in the breadth of sun circulation, regardless the chosen period. And we think that these results help us reconcile, at least to some extent, our theoretical understanding, which is the acceleration of the breadth of sun circulation due to climate change, with recent estimates from observations and reanalysis. And finally, we explore the potential impact of this low frequency variability in ozone levels in the tropical middle stratosphere. So the top panel shows the time series of 10-year running mean ozone in the tropical middle stratosphere as simulated and observed. And the lower panel shows the observed low-pass filter IPO index for the whole time of the simulation. And we can see how these negative trends in ozone and relatively low levels since year 2000 are in agreement with the potential mechanism. That is, this cooling in the tropical Pacific is associated with a relatively weaker breadth of sun circulation that enhance the breakdown of nitrous oxide into reactive species, enhancing ozone loss rates. But of course, there could be other drivers, such as long-lived halogens or changes in emission of nitrous oxide abundances or major volcanic eruptions. So we test those key drivers by running a series of sensitivity simulations. And if we assume that these drivers affect ozone linearly, we could see that nitrous oxide and long-lived halogens can explain up to a fifth of the recent trend. Then major volcanic eruptions can explain another quarter of the recent trend, but it's internally generated variability in the sea surface temperature that explain most of the recent trends in ozone levels. Now, if we focus on the simulation where we fix long-lived halogens at the beginning of the simulation, we see as expected that there is no long-term decline in ozone, but what we can see is a very clear IPO-like signal, explaining very little of the recent trends. Now, if we focus on the simulation where we imposed climatological sea surface temperature, we see as expected the long-term decline in ozone, but now the simulation doesn't completely get decadal variability as in the base simulation, and that is what explains this half of the trend in ozone. So to summarize or conclude the presentation, we have explored and showed that multi-decadal variability in the breadth of sun circulation associated with the Pacific Ocean can help us better understand structural changes in the breadth of sun circulation over the recent past. Also, via a series of sensitivity simulation, we showed that this decline in tropical mid-stratospheric ozone in the 90s and relatively low levels in year 2000, they are not primarily driven by anthropogenic perturbations, but rather by natural variability in sea surface temperatures. So I think this is all, and thank you so much for having me here today.
Thanks, Fernando. Does anyone have any questions?
Let's see if I can get
those are big numbers for decadal changes, like 15% per decade. Mechanistically,
I don't see the chat.
Oh, I don't see any questions in the chat right now.
Okay.
I was going to ask, so numbers like 15% per decade are quite a big trend, especially over the observational period. So do you have an idea mechanistically of how this is damping the trend, like physically, how the IPL variability masks that?
So this is the first work we are doing with this, and back in the time when we started doing this work, we also started looking whether this signal was present in different climate models. And for that, we used two different CIMIC-5 models that included interactive chemistry, and found a weaker signal, but the signal was there and was significant. And then we thought whether we should go to look into these changes into comparison study, or whether to look into how these changes impact the Brute Dobson circulation over the recent past. And we chose to go for that road at the beginning because we were running WACCM and we could run sensitivity simulations to support this finding. So, and there is much more work that can be done, and this is something that we could look in follow-up studies, what models, what is important to capture this natural variability in different models, what are the key parameters, what are the key components to be able to better understand this natural variability.
Yeah, that's cool. That's cool to see that it's robust across models. Thank you very much. There's no other questions. Let's move on to our next speaker, Joan Alexander from Northwest Research Associates.
You good?
Yep.
Okay, so this is about observational validation of the tropical gravity wave parameterization in WACCM 6, and some very recent results relevant to resolvable wave driving of the QBO from superpressure balloons. And I was hoping to spawn some discussion on trade-offs between vertical resolution and improving gravity wave parameterization with this talk. So to map what I'm going to show, using observations from the long duration balloons to validate or compare to the Barris convective gravity wave scheme in the tropics. So looking at momentum fluxes there to see what we can learn. And then we're also running that Barris scheme offline using TRIM to define the convective sources instead of the Zhang-McFarlane convective parameterization parameters. And finally, we look at TRIM cloud and latent heating properties that are relevant to this parameterization and compare those to the Zhang-McFarlane convection. And this last bit, which I'm going to have trouble getting to, I think, in the time allotted, are some new results from balloons on resolvable, theoretically, large-scale gravity waves that are suggesting we would need really, really high vertical resolution to resolve realistic mean flow interactions. And so as a compromise, where do we, I also offer some possible changes to the Barris scheme to improve the representation of unresolved wave driving, which might include these large scale, short vertical wavelength gravity waves. So first I'll just give my summary of how the Bear scheme works and define a couple of the key parameters here. And so I've got this diagram to kind of show it. The scheme feeds off the Zhang-McFarland convection scheme. And key parameters are the heating profile and the maximum in that heating profile and the depth of that heating where it's positive. And then the winds, the resolved winds in the grid scale are also really important, especially this mean wind in the heating layer and static stability. So you take the grid scale heating, which is Q, and you divide it by a convective fraction, which is just set to be 5% right now. And that gives you the subgrid scale convective heating. That gets squared to derive a momentum flux for the gravity waves. And a lookup table is read in that depends on this BQ wind and the depth. And then there's also a bunch of other parameters, including some tuning parameters out in front. And then the force
I'm still seeing the first slide.
Really?
I'm seeing what you're showing, Joan. It looks good to me.
Okay.
Okay, sorry.
It's got a yellow banner.
Yeah, we
Okay.
can-
Bear scheme for tropical gravity waves.
Thanks. Okay, I'm sorry, someone's having trouble. So then the force on the mean flow is just the vertical gradient in the total flux in the spectrum, and divided by density gives you the force with an efficiency factor. So a bit about how WACCM tunes right now, at least in WACCM 6. And this started back in, some of these go all the way back in time, and some of them date back to WACCM 5. So this, like I said, this convection fraction is 5% everywhere. And since WACCM 5, that depth parameter was scaled by a factor of 4, so a big scale factor, and in order to look up this, in order to retrieve this spectrum from the lookup table. And that, that depth parameter is more or less, if you work through the dispersion relation, is more or less proportional to the phase speed where the peak fluxes occur in the spectrum. And so dividing depth by 4 reduces the phase speeds in your spectrum. So apparently to get a QBO, which is why this was done, they needed lower phase speeds and all our higher amplitudes. Because here's what happens in the lookup table if you read in a phase speed spectrum with a depth of 12, and then all other things being equal except for the depth being divided by a factor of 4, it shifts the spectrum to these much lower phase speeds, and you get larger amplitudes in those waves. And here, as I mentioned, this efficiency factor is another tuning parameter for the scheme. So let's try to do our first validation, look at just the momentum fluxes that occur in the Bear scheme. And we're using WACCM SD because we have this balloon observations for a certain 3-month period in 2010. So we run it in SD mode so we get the winds right, which are really important for doing this kind of comparison. And this is just a distribution of how frequently waves with different fluxes occur. And it's pretty clear that the WACCM parameterization just does not have any of these really large fluxes that are occurring in the pre-Concordiazzi balloons. And the zonal mean of those zonal fluxes is also about 1/3 of what we're getting from the pre-Concordiazzi balloons. So the zonal mean fluxes are also weaker. So that's a first comparison. And then if we ran the Bear scheme offline, using instead of Zhang-McFarland heating with the tuning parameters that were assumed, and instead use heating parameters from TRIM, the SLH latent heating data product from TRIM, you get a much longer tail and higher fluxes. And so it suggests that we should look at the heating. And that's what I'm going to do next. So here's the WACCM subgrid scale heating rates and their probability of occurrence. and the TRIM subgrid scale heating rates and their probability of occurrence. And note that the scales here are a factor of 10 different. So WACCM, with its convective fraction of 0.05 or 5%, is just not having any of these high heating rates that we think should be there based on TRIM. So that's obviously something we could change. And if you do just make a simple change, we just reduce this convective fraction, which is pretty defensible, I think, to reduce it to 3%. And if we don't try to do any corrections for the scale observed and just treat a single pixel from TRIM as the Q0, it brings these two into pretty good agreement in comparison. So that would be an obvious thing to do to that this observational comparison suggests. And then here now we're looking at, since we think we should look at the heating, here's a distribution as a function of depth and this subgrid scale heating rate. In WACCM 6, land and ocean are separated just for convenience or in case there are differences. And then here's from the TRIM data product. And here I've used this convective fraction of 3% in order to see how that would improve things. And it does really improve the distribution of heating rates. You get much closer to the observed range. And then this is not including the division by 4 of the depth that was tuned in WACCM 5 and 6. And you can see the range of depths in the Diane-McFarlane scheme is comparable to the range of depths seen in TRIM. So there's no support here for dividing the depths by a factor of 4 in particular. So now let's look at the momentum flux phase speed spectrum. This is an important parameterization. It determines sort of the speed of the QBO and where the waves will break and how the waves drive the QBO. So we're going to look at the zonal mean zonal flux spectrum. This green line is from the balloons, and the red line is from the tuned WACCM 6 with the D/4 parameter. And you can see that shifting where the WACCM 6 is all concentrated at lower phase speeds. Because compared to Barris, which is fed TRIM latent heating parameters, that's the blue line. And so it's filling out the high phase speed part of this curve. So neither of these is the same as the observations, but the red curve, obviously, WACCM 6 is missing the high phase speed rate waves that would apparently be influencing the atmosphere above the QBO, which in WACCM you care about. So where are these low phase speed waves? If we shouldn't divide by 4, because the observations don't support that, where are they coming from? I don't have time to explain this slide at all. It's about the mechanism a mechanism that's sort of missing in the current Barris scheme, but I'm gonna just skip this slide. Yaga actually included in her original paper formulas for this stationary wave component that is missing currently. It wasn't included in WACCM, it's never been included, but it could be. And it's basically when there's shear at the top of the heating, you get this strong wave emission and the phase speeds match the motion of the convective cells. So we coded that up and looked at what TRIM would predict for this spectrum of waves. We don't know the absolute units of the momentum flux. This is the normalized units, but it does concentrate in these low phase speeds, and it's likely to give larger amplitudes based on mesoscale model simulations. So we think that this could be added, and together with the traditional parameterization, it could really give better results. And so the last thing I'd like to show is just this result from really just this one slide from this paper I did with Bob Vincent recently, where we zoomed in on a case study from a superpressure balloon. The previous results were all looking at the higher frequency waves, and here we're looking at very long period gravity waves, and they turned out to have large scales. And there was a 1-day and 3-day gravity wave events that were apparent in the balloon trajectory. Also, you can kind of see the Stokes drift patterns in the balloon trajectory. And the analysis showed us a 1-day period gravity wave with a horizontal wavelength of about 1,000 kilometers, so potentially resolvable. But it was observed at a level where it would reach a critical level within 600 meters above the balloon. So there's no way a model, even with 500-meter resolution, would be able to capture this wave at the level where we observed it. And the zonal mean forces that we estimated, even accounting for the limited area of the wave, which would include a limited area of forcing, even if you account for that, these numbers for the force on the mean flow are quite large. They're a large fraction of the total needed to drive the QBO, at least for the duration of this event, which is about a day. And so just the key point is that these large scale, potentially resolvable gravity waves drive the lower stratospheric QBO near wave critical levels, where these vertical wavelengths are getting very short. And this dissipation closer to critical levels is going to give larger forces. The density will be lower, so this is in the denominator. So you could get about a 50% boost just for a few kilometers, delaying the dissipation. And also that if the depth over which you dissipate is shallower, which it would be between, with a critical level only 600 meters above you, we could have errors in the forces of several factors. So just in summary, to get realistic forces from resolved waves would require very high vertical resolution, impractically high, and the Bayer scheme changes could make the tropical wave forcing of the QBO much more realistic. Some fairly simple changes that I outlined. And so maybe there's a trade-off here in choosing your vertical resolution and improving your gravity wave parameterization. Thanks. Any questions if there's time?
Yeah, there was a question there's some questions in the chat. If you guys want to just ask those, feel free.
Yeah, like others, I'm having trouble seeing the chat, so please speak up.
Julio wants to know, what was the phase speed of the long wave that was observed?
It was, let's see. So
Yeah,
it was
that wave that you see, it looks like it's
Yeah.
near Meaty.
Yeah, it was, I didn't write it down here, but it was less than 10 meters a second westward. Does that answer your question?
Yeah.
So we observed it sort of here. This is the time height profile of the zonal mean winds. And the critical level was about 20 kilometers. And the wind there is about -10. So might have been -10.
I guess I would just argue, I mean, I know that higher vertical resolution is always better, but I think the waves are going to break down using parameterized processes anyway. So I think we should talk about that. The breakdown's not going to be it's not going to be well resolved in any case.
Right. Yeah, I agree with you.
This is good food for the discussion, 10:30. If there's no other quick questions, thank you, Joan, and we can move on to Simone, who's going to talk about sensitivity of climate intervention, stratospheric sulfur injections on stratospheric ozone.
Sorry, I couldn't unmute myself while I was screen sharing. I didn't know how to do that now. Okay, can you see the presentation now and hear me? Okay, sorry for that. Okay, yeah, so first I want to thank my contributors and co-authors listed here. And I want to talk about impacts of climate interventions on stratospheric ozone. How do I excipient? Here we go. So, I mean, this topic has been addressed before, but with increasing interest in climate intervention and people really want to consider or look into these options, we do need to know what potential effects are, and especially the effects on stratospheric ozone. So here is a view of the last WMO assessment for ozone depletion 2018, and we did have a section on the topic, and it was briefly mentioned. There are still some open question on how stratospheric ozone would be altered with different options and strategies. And so now for the WNO 2022, for the first time, there will be actually a chapter on stratospheric aerosol interventions on ozone. And one of the important topics is really what are the effects on ozone? And that depends on the way how these applications would be, or the specifics of the applications, the amount, the timing, location, and what type of potential aerosols. And so the study I'm presenting here is looking into the question on the effects of different injection locations. And so what we are using is the WACCM model, the version based on CAM 5.4. So this is before the club scheme was introduced. And this is also the version that we used for the geoengineering large ensemble simulations. I'm also showing results not only from the 70-layer model, but also from the 110-layer model. This model has the prognostic volcanoes and aerosol microphysics, has middle atmosphere chemistry, and is coupled to the ocean and land and so on. So there are new studies also with WACCM 6, for example, for GeoMIP, peak shaving scenarios, as well as scenarios that go from the SSP 8.5 to 4.5, and new simulations are being set up on SSP 4.5 to reduce to 1.5 temperature targets. But I'm not talking about those here. And if you're interested to learn more about it, let me know and connect, please. So this study is about different injection experiments. And so what we did was we performed the geoengineering large ensemble or GLEN simulations, which has 20 members. And we were injecting sulfur at different latitudes, 30 north, 30 south, and 15 north, 15 south, above about 6 kilometers of the tropopause. And the reason was that we want to modulate the injection amounts so we can control and keep surface temperature at certain levels globally, but also interhemispheric differences in equator to pole gradients. And we also performed then other simulations. One is the equator injections only. So this contrasts if you don't actually modulate between different latitudes, these injections. We also did injections at lower altitudes, so only 1 kilometer above the tropopause. And then finally, we did one ensemble member of a 110-layer model that Yaga and Rolando had developed. And so what we can see here is that these simulations actually achieve the goals of keeping surface temperatures from changing from 2020 conditions. So starting from 2020, we have an RCP 8.5 high forcing scenario. Then we continuously inject sulfur and increase the amount steadily. So we would keep the temperatures. And as I said, not only the global temperatures, but also the interhemispheric temperature gradient and the equator to pole gradient. And what we can see is that only the equator injection case, while keeping the global temperature to those levels, we cannot really keep the equator to pole temperature gradient because we're not modulating this. So if you look at the burden now for sulfate after time of injection here in 2080 to 2089, you can see the injection locations, and the burden is looking quite different. For the higher injection case, you see a higher expansion of the burden, while for the lower, it's more below and denser. The equator injection has a much more refined burden in the tropics. And interestingly, we do get different results for the 110 layer model. We do see not such a large difference between the different hemispheres. For Glens, we had to inject more in the northern hemisphere, while this is more equal in the 110 layer model. If you look at the burdens and also at the burden to the injection rates here, you can see that you need quite a bit of different injection amounts, which results also in different burdens. So for the low injection case, we need by the end of the century up to 80 teragram SO2 injections annually. And this is because there's a much more faster exchange and the lifetime is shorter. So aerosols will go and deposit faster, get removed faster, being closer to the tropopause. While on the other hand, the equator case also needs a bunch of more injection compared to the Glens scenario, because there is just more refined aerosols in the tropics and more sedimentation. Interestingly, the 110 layer model does need a bit less of injection. So potentially having a model that is a higher vertical resolution will cause or require less injection because of more refined gradient across the tropopause and next edge change. But so the questions we want to ask is, which cases will show the largest ozone impact on ozone? How will a steady increase in sulfur burn impact stratospheric ozone? And will chlorine decline reduce the change in stratospheric sulfur injection? And so looking at the general impacts on actually the stratosphere, this is just the schematic showing what is happening if we have a advanced sulfate distribution. Here's an example for Glens in the end of the injection, so 2080 to 2089. You do see that surface area density is certainly increasing as well, but not in the same way. You see different patterns. For example, you do see much higher increase in high latitudes. And this is because the surface area density is not only dependent on the mass, but on the size of the particles. And so if we have smaller particles in higher latitudes, we do get a higher impact there, which also reacts then on the heterogeneous reactions and changes the chemistry. Also, the higher burden will increase the radiative heating, and you see the temperature change here on the bottom, which also changes the tropopause height. And with the warming of the tropopause, we see increases in water vapor. We see also increases in advection and zonal wind changes. We get a strengthening of the especially southern hemisphere polar vortex, weakening of the subtropical jets, and changes in horizontal advection, as well as in vertical advection. And all these changes combined will lead then to changes in ozone, which are actually not quite the same as the net chemical changes, which are shown here. I don't know if you see my mouse or cursor, probably not. But on the third row top panel, what you can see is the net chemical ozone production in the background colors, and then the change of the heterogeneous cycles as the symbols here. So the Hawks, clocks, and Brock's catalytic cycle is increased, so it's red, which then causes the net chemical ozone production to reduce. However, on the other hand, the NOx cycle is actually decreased because of hydrolysis of NOx to N2O5, which reduces NO2 and therefore reduces that cycle. And we do get actually an increase in net chemical ozone production. But what is interesting is that the changes in ozone are not only, as I said, caused by the chemistry, but also strongly impacted by the dynamics. So if we do get less upwelling as a result of these injections, we do get more ozone in the lower tropical stratosphere. And also if we get more exchange towards higher latitude, the increase in ozone due to the reduced NOx cycles do also show up in higher latitudes. And so we can look at many different things, and you can imagine that having different strategies, all these cycles will change, or these different factors change somewhat depending on the distribution. And I want to focus now on the polar regions here. What you can see is the total column ozone. Here shown on the left top, you see the decrease during the ozone hole season. There are some observations. So we in general reproduce the observation quite well. And then you see the recovery by 2040, and then a super recovery toward the end of the century. And when you look at the injection cases, experiments, what we see is a drop in ozone happening abruptly. And then we see some changes between the different scenarios. So this is a bit to explain, but just briefly, some examples, for instance, for the equator injections. Well, as I said, we need more injections and we have a larger burden, as we can see here. We also have stronger increase in water vapor, which we'll think would increase heterogeneous reaction rates. But then a very strong effect is really the strengthening of the polar vortex that is stronger compared to the Glenn simulation, as well as contributing is the shutdown of the QBO. So we do see stronger ozone loss in this case. For the low injection case, we do have much more, we require much more injections, but we get about the same aerosol burden, though the burden distribution is different. We do see strong increase in water vapor, but in general, the vortex is not as strongly, not so much enhanced as for the Glenn scenario. And so we do see more horizontal advection and in general, a reduction. So there are subtle changes between those cases. Interestingly, is also that the 110 layer model is showing a little bit less ozone depletion than the other models, partly because it does require less injection here, but it's also because of actually how the aerosol are distributed between the northern and southern hemisphere. So the question then comes up to me, what is actually causing this abrupt decrease in ozone for the first 10 years? We're slowly increasing the injection rate. So we would expect that maybe we get a slow increase in ozone depletion, but this is not the case. And looking at these more, what you can see here on the top is actually the difference here in Dobson units as a result of the injection scenarios divided by the injection amount. And what you can see is that when we start geoengineering, we get an abrupt increase in the efficiency of the ozone depleting, ozone reduction here. So a strong drop, and then with increased injections, we'll get less and less relative depletion of ozone. This is the case for all the different scenarios, but of course it depends on the amount of injection, how strong the signal is. And the reason is actually why we see it has to do with changes in the surface area density. Here we're picking the area in the polar region, also between 60 and 90 south in the lower stratosphere in September, October, November, and you really see this very strong increase in surface area density for all these cases, independent on what injection scenario we have, but then we see that more steady increase with time. So no matter when we start geoengineering, actually, and we've seen it in another also study, we do get an abrupt decrease of ozone, which will have an impact, of course, on the Dobson units and on UV and other things. Looking now quickly at—
Hey, Simone, we've got just a couple minutes.
Yes, sorry, I will do this. So in March, we don't see that strong effect. It's also that this—
Can you share your screen again? Sorry.
Oh, I stopped that. Sorry,
That's not good.
I pressed the wrong button. Sorry for that. Okay, can you see it?
Yeah.
Okay, so yeah, in March, this effect isn't that strongly visible. There is a stronger effect on the dynamics. The area is more dynamically active. And looking even in January or at the tropics, we talked about the super recovery. And so without geoengineering, we do see a strong increase in the RCP 8.5 scenario in January in the mid-latitudes. That is much higher than what we have seen before in our history. And with geoengineering, we actually even see an increase of ozone in this region. So there's the question, how actually, how much does this change impact life on Earth? Changes in UV may decrease, and also that is a problem potentially for plants and ecosystems. And finally, I think I should quickly wrap up just to show that really the change between the early change in 2030 to 2039 compared to present day for the different scenarios, it's not too different. We do see the reduction in October that I outlined, but there are some changes. So it is important to understand the differences and to also understand the model differences in using a 110 level model versus an 80 level model. And just to quickly say some words for future needs. Well, we do need to look at different models, and we do have new CCMI experiments that will look at that. We need to hopefully improve the 110 layer model, the fix in the water vapor, which is important to see if we do get other results also for these injection experiments. And it's important to look at UV changes that are a result of these changes on column ozone, and especially identify the impacts on ecosystems. And finally, we are working on a new sectional aerosol model scheme, the CARMA model, to implement here, and it will be really interesting to see how this effects will change when you have a new scheme like that. And with that, I stop. Thank you for your patience.
Thanks, Simone. We have a quick question in the chat. I don't know if you can see it.
So there's one by Chuck. You want to tell me what it says?
Dan's got a question. I think Chuck just had more of a comment. Let's just, if we can just take Dan's and then move on, that would be good. How much of the tropical lower stratospheric warming is coming from the ozone change in that region?
I think it's mainly coming from the sulfates that are increased. And so the ozone change is smaller. It's, I would say, a secondary effect, but it is a small effect. Okay,
cool. Yeah, if you want to have a discussion with Chuck, possibly in the chat, we're going to move on to Nick Petitella, who's our last speaker, and he's going to talk about CESM2 WACCM subseasonal forecasts.
All right. Can you see the slides? Okay.
No. Don't see a screen share from you.
I think I forgot to share the screen.
There we go.
All right, you can see them now?
Yep.
Okay, yeah, so I'll present a bit about this CESM2 subseasonal seasonal simulations. I'll give some results both from CAM and from WACCM as well. And these are from a project largely led by Jager Richter with a larger team involved as well. So just as a brief summary of the setup for these simulations, we will show some that are from CAM, but really try to highlight the ones from WACCM. And so these are based on the WACCM 6. So we have 1 degree horizontal resolution. And unique thing about these experiments is that they are, I would say the first subseasonal to seasonal with a model top that extends into the thermosphere, which allows to look at some higher altitude predictability, which is I think the first time we could do this. And these there's two sets of experiments. One is a set of hindcasts that were performed from October to March and cover the period 1999 to 2020. And here on the right shows the kind of setup in terms of initialization. So for the WACCM, they're initialized off of MIRA-2, and CFS, the climate forecast system, is used for CAM. The reason for the difference is partly so that we could do real-time or near real-time forecasts using WACCM that was not necessary for CAM. And then they also have a land and ocean initialization. And for the hindcasts, they're based on 5 ensemble members for WACCM, and then the forecasts are using a 21-member ensemble and slightly larger ensemble number used for CAM. And as I said, these are now running in real time, and I will show some results towards the end related to the forecasting the recent sudden stratospheric warming in WACCM. So the initialization, as I said, is based off of MIRA for WACCM, and just one comment on how these ensembles are generated. For these experiments, they all use this so-called random field perturbations as opposed to an initial condition perturbation. And this is really to improve the spread of the ensemble in the initial forecast period. So on the left here is the ensemble spread in these solid lines for 500 hectopascal geopotential height. And the red shows the ensemble spread using this random field perturbation versus the blue, just an initial condition perturbation. And you can see in the blue, you really do not get much ensemble spread for several weeks, which limits the usefulness of the ensemble during the initial part of the forecast. And this is partly improved when you do the random field perturbation. And you can see this here in terms of dynamical variables. Here is the zonal mean, zonal wind at 10 hectopascal and 60 north. And this kind of thinner orange lines are the ensemble members initialized using the random field perturbation. And you can see initially there is kind of a diversity among ensemble members leading to this stratospheric warming event. Whereas in the light blue, you really do not see any diversity among ensemble members until later on, several weeks later. So this is why we use this random field perturbation method for the initialization. So looking at first just some of the predictability of the surface. So here is surface temperature anomaly correlation coefficient for Northern Hemisphere winter. And here, all of these are a similar style of plot where they're divided into the weeks 1 to 2, 3 to 4, and 5 to 6 forecasts. And then the different colored bars are different, either WACCM, CSM2 with CAM, and then a previous set of simulations performed by Yaga and others that were using CSM1. And here you can see there really is not too much difference in terms of the skill in terms of predicting either surface temperature or total precipitation among these different models. So even the higher top in WACCM doesn't really provide too much benefit in terms of these metrics. Looking at the spatial patterns here, what's shown as again divided into different forecast periods, weeks 1 to 2 on the top, 3 to 4 in the middle panels, and then 5 to 6 on the bottom. And the left here is the anomaly correlation coefficient for surface temperature, CSM2. This is CAM, And then here are differences between CSM2 and CSM1, and then CAM and WACCM in terms of CSM2. And again, you see maybe some small regional differences, but there's no, I would say, dramatic differences among the different versions of the model when looking at the surface temperature forecast or hindcast. And then looking at some of the modes of variability, here on the left is looking at the North Atlantic oscillation, again in Northern Hemisphere winter months. And this is an aspect where we may expect perhaps some enhanced skill of having the well-resolved stratosphere in WACCM. And you do see potentially at weeks 3 to 4 in the analysis of the hindcast experiments, WACCM in the blue here does quite well. So it may be potentially best, keeping in mind that there's only 5 ensemble members versus 10 here for CAM. But it turns out this is not a statistically significant difference due to the kind of limited nature of these ensemble experiments. So it may be better in terms of predicting the NAO, but not at least statistically significant based on these experiments, and similar for slightly longer lead time. And looking at the MJO prediction skill here is CSM1 in red with 20 ensemble members, and then CSM2 with 11, and they're fairly comparable in terms of the skill for predicting the MJO. And as I said, one of the unique aspects for CSM2 with WACCM is that we can look at predictability in the mesosphere and lower thermosphere. And this is of interest largely in terms of how this would couple into, say, geospace or ionosphere, thermosphere predictability. So what is shown here is these are the Northern Hemisphere polar cap temperatures. And these are a composite of 14 major sudden stratospheric warming events that were included in the hindcast period. And the upper left panel here is the composite based on some specified dynamics simulations, which can be treated in some sense as verification fields. Since we don't have something else that can really be used for that, we are using a model simulation. So it's not the ideal source of verification here, but that's what's available. And you can see a few aspects in terms of the middle atmosphere changes that occur during sudden stratospheric warmings. You see this kind of cooling of the mesosphere and lower thermosphere right around the time of the warming. And then there's also this kind of a stratopause jump, which you can see in the dashed line here, say a week or so after the warming. And then the other panels are the composite of hindcasts in WACCM initialized at different lags. So this first one is initialized 30 days prior to the onset of the stratosphere warming, which I defined as the reversal of the zonal mean zonal winds. And you can see there's essentially no, at that far in advance, no changes that you see in the middle atmosphere or indication of the stratosphere warming. But as you do get closer to the warming, you do, of course, predict the stratospheric warming itself with a lead time of something around 5 to 10 days, which is consistent with other analysis of other models. But a unique aspect here that we can highlight is that it does predict some cooling of the mesosphere in these hindcasts that are initialized, say 20 days or so prior to the warming. And then the later ones also are able to predict this sort of jump in the stratopause that occurs following the warming. Another aspect that we've looked at is the tidal variability in the experiments. So what this plot here shows is the amplitude of the migrating semidiurnal tide And it's well known that this becomes enhanced during sudden stratospheric warmings and is an important source that couples stratosphere warmings to variability in the ionosphere. So to the extent that we can predict this variability as potential for improving space weather forecasting. And here is so the SD WACCM is in the dash black, and climatology of the semi-diurnal tide is shown here. So there you can see this large enhancement that occurs around the stratosphere warming in what we use for verification. And then the different colored lines are basically the composite of the hindcast, again, initialized at different points. And you can see prior and near the onset of the warming, you do capture this elevated semi-diurnal tide and some sense of the increase, but they all tend to decrease a little bit too quickly. And it appears that this might be due to basically the winds reversing faster in the model compared to what we see in the analysis used for verification. But it is encouraging that there is some sort of, at least for several days, skill in predicting this tidal variability, which would imply, again, that there is some associated skill in predicting the ionosphere variability that comes along with that. And then just briefly to conclude, just show a few panels here showing analysis of the recent sudden stratospheric warming and the basically near real-time forecasts. So these plots all show the same parameter, which is a zonal mean zonal wind at 60 north and 10 hectopascal. And they're all the same setup. So the black is basically a verification field from a version of Mira available in real time. And then the thin lines are the ensembles, and then the solid blue is the ensemble mean. And these are just initialized at different dates, which is the difference among the panels. And you can see this stratosphere warming occurred in early January, and these forecasts in WACCM did a reasonable job predicting early and quite a good job of tracking these sort of changes throughout the life cycle of this recent SSW. And here are the most recent forecasts initialized just in the last few weeks. And you can see again that the near real-time WACCM forecasts did quite well in terms of predicting the stratosphere. And I think Yaga and others are, now that it's been about a month since the stratosphere warming, starting to look at the surface verification as well in terms of how well the model performed at these sort of month-long time frame in terms of surface variability. And so just as conclusion, these, especially the WACCM hindcasts and forecasts, are really, I think, the first extensive set of the subseasonal to seasonal simulations in a model with an upper boundary in the lower thermosphere, which makes them, I think, rather unique. And all of these will be released, both CAM and WACCM, the full ensembles, to the community, so anyone can have access to these for various investigations. And they're currently in progress to make them available via the Climate Data Gateway. But anyone who does have access currently to Cheyenne, these data can be made available to you for any analysis. And then the framework that was established here can be used for future predictability research, and there's been some work beginning to use this for seasonal to decadal predictions.
All right, thanks, Nick. There's a few questions in the chat, maybe some easy to answer ones. I don't know if you can.
I can't see it.
Okay.
But I can exit this slideshow maybe and try to find the window.
Nick, I had a couple of
It's maybe easier if you
clarification
just
questions. One was, how was the MJO skill measured? I noticed the skill was already less than 1 at lag 0.
This, I don't know exactly how this analysis was done. I did not do this part of it. Yaga may know. I see she
Yeah,
is.
that's an RM scale. It's based on an RML scale, and it's a little less than 1 because we're not, actually, we're not exactly initializing, right? We have to, our ocean is a little different. The atmosphere is a little different. So yeah, I think you just seeing that a little bit of initialization shock, etc.
Okay. And then the other clarification was I missed what was the altitude where you evaluated the SW2 tide during sudden warmings?
This was 10 to the -4.
Thank you.
I had a quick clarification question on this the slide you just showed.
On this one?
Yeah. I just want, you're saying that none of the differences aren't significant. Is that, does that hold for, I mean, it looks like there's a pretty large difference between the CSM WACCM ensemble, 5-member ensemble, and the CSM2 CAM ensemble. That's not significant either, those?
So yeah, we did the testing with using a Fisher Z transform, which is what we thought was, you know, it's a common test, statistical significant test. And because we only have 20 years of hindcast data, it did not show to be significant. So partly, I think it's sampling issue. I don't know. We don't know whether there is a real difference there. But yeah, that's the test we use. We can, that's the one that it's been recommended to us by when we wrote a paper about it for S2S with CSM1, and that does not show any significant differences.
Hey, Nick, I have a question. So you mentioned the wind is reversing too fast, and that may, affect the SW2. Are you referring to the stratosphere wind or the MLT wind, or both?
So primarily the MLT wind. So you see a very similar sort of, if you plotted, the wind in the mesosphere, you would see a very similar where the verification kind of is much more gradual versus in the hindcasts. And that's true. I did actually also look at specified dynamics for WACCM 6, and it shows the same thing. So it's not related to sort of model differences itself. It seems to be just something different between the hindcasts and the analysis fields.
Okay, thanks.
All right, let's move on to the discussion, which we've probably got about 20 minutes for. We don't want to keep anyone too long this morning. I think probably I'm guessing the most, one of the more important things to talk about is the gravity wave parameterization stuff. And I am definitely not the person to talk about that. So I don't know if Julio or I think Adam, I saw comments from Adam in the chat too during Joan's presentation, but it would be worth talking about that here while we've got everyone's attention and everything's fresh in everybody's mind.
Maybe I could just say one thing real quickly.
Sure.
If you did want to improve the parameterization, I think the coding would be pretty simple, but of course the job is the tuning. And I think this is one of these instances, another one of these instances where the research community has a timescale that's based on getting projects funded, and you guys have your own timescale, and they're never meshing up right. So it's too bad.
I'll just expand on the question that I had about the area of the grid cell occupied by convection, which you show improves the heating rates when you lower it from 5% to 3%. And I was just posing the question, you know, we have a couple estimates of the convective area fraction throughout the model. One of them is for using the estimating the area for purposes of radiation. And that uses a sort of an empirical calculation as a function of convective mass fluxes. And since I asked the question, I plotted out what the typical area fraction is. And long story short, it tends to be an order of magnitude larger than what you think is appropriate for an order of magnitude larger than 3%. It's on the order of 10% to 20%. So probably not worth making those two schemes consistent.
Well, I think you have to keep in mind that what the gravity wave parameterization is trying to describe is pretty different from what affects the radiation. We're trying to describe the very most intense rain plumes, you know, the very most intense rain and the very most intense latent heat release. And those tend to be pretty small scale, even, you know, within a convective cloud. So I think that there is a difference here. I wonder if maybe you could use that measure to provide some variability in that parameter, but you wouldn't want to just pick the same number, I don't think.
Yeah, so there's a tuning constant we use that pretty much sets the order of magnitude. And right now that tuning constant is set to 10%. So you could use the same equation and use a tuning constant of 1% or 3. And that would provide you with the variability you need, or variability that might be desirable. But I think you make a good point. We want to know, but in the radiation, we want to know the ensemble convective cloud area. It sounds like you just want to sort of pick out maybe the most juiciest member of the ensemble.
That's pretty much correct, I think. It's a good way to say it, another way to say it.
I just want to get clarification from you, Joan. The missing source that you're talking about is what's often called the moving mountain source.
Right. It's the stationary component of the heating, which isn't included in the parameterization.
Right.
So you're moving with the cell.
Mm-hmm. So it's the air sort of moving up and over and around convective powers.
Right. That's the linearized
right.
concept in our minds. Yeah. We do see it though in nonlinear mesoscale model simulations. It is a real thing, I think. And some evidence in observations as well. I wanted to also say that, you know, this idea of these resolvable waves, which are pretty large scale but have very short vertical scales. I referred to this Bob Vincent's paper earlier this year, but we have additional evidence. It's just not published work yet from the recent Stradial 2 balloon campaign. We're seeing this frequently, where we have these large scale waves with very short, large scale and slow sort of gravity waves that have very short vertical structure. And when you calculate the likely forces on the QBO, they're pretty large. So I don't think it's just a one-off case. I think it's at least, we have at least several cases so far. Might be quite common.
And this has the vertical wavelengths on the order of like 600 meters you were showing.
600 to 700 meters. And then, you know, Kelvin waves with a few kilometer vertical wavelengths, 3 kilometer vertical wavelengths.
Dan, is your hand up for right now, or was that from earlier?
No, it's for now.
Okay, all right.
I just a comment that it's probably worth pointing out that we're going to have this regional refined capability, and maybe this is another way, that we're going to be able to look at developing parameterizations of the for gravity waves by kind of adding a lot of resolution in a small area, then using that to inform our tuning of the gravity wave parameterization.
Yeah, I mean, we won't have 600. We won't have probably the vertical resolution to resolve something with 600 meter vertical wavelength, but yeah, I actually, we're sort of at the stage now where we can do little test simulations that are seemingly stable at like 8th degree refinement. And I think probably in the next month, we'll be looking at some of the output from that just to get a handle on it. I think it would be good to combine this with an observational analysis, because it's kind of like, it'd be nice to let the model do its thing and figure out what it wants to resolve. But in the end, it's still going to have its own biases and things too. But yeah, I agree. The regionally refined simulations, I think, are going to be really useful, especially for understanding transport too by these waves. But
yeah, getting it. What's the problem of the parameterization, and what's the problem of actually the sources used to drive the parameterization?
Yeah, the output's big though. I did a 5-day test and saved every time step output just to be able to look at everything that's coming out of the model. And this is the sort of thing where if we're going to engage community members also to get involved, I know Joan had contacted you earlier about this, but it's enough that we'll really have to coordinate well if you want to take a peek at sort of the native, cubed sphere grid output, because we can't hold on to it very long. I think 5 days, it's, we're churning out 1 terabyte a day of data from the model, and that's with a super reduced output field. So if you're interested in looking at that, I know some other folks at this meeting are too, we should all coordinate. So if you are interested in looking at output from WACCM regionally refined at 110 levels, you can drop me an email. It's going to move pretty fast though, for sure. Again, because we can't hold on to everything.
So for example, if there was a period, we could let you know that you could store it somewhere longer term?
Yeah, I mean,
period or something?
Yeah, it kind of depends how much output you'd be interested in. I think for right now, we're trying to nail down, for the especially transport and like the MLT, do we actually need to save the every time step data to get good numbers on that, or can we truncate that? But for sure, for the meteorology, I want to save like U, V, T, omega, things like that every time step on that global grid. So I think, it's possible. It depends, because the model throughput will be a big bottleneck for this. So it's possible that we could, at minimum, hold on to it for, a few months, and then we may need to get creative about what to do with the data. But yeah.
And we only have it over CONUS, so just be aware if you're looking for a fixed one. We're not doing it over Hector or your favorite area.
Yeah, we haven't come, although it'd be cool to do a tropical mesh sometime, but yeah.
I'll point out, just real quick, Chris Cruz and other people, I think, that may be on this call are working on regionally refined simulations over South America, which will be done at not only high horizontal resolution down to 3 kilometers, but also high vertical resolution to match WRF. So this is with an hydrostatic dicore, so, take it as you want, but it will be directly comparable to some WRF simulations that'll be done for the same project. So I'm not sure how high the model top's going to be in WRF, but we'll be using the, perhaps too low, 40 kilometer-ish top for the CAM simulations. Yep, Chris says it's a 40 kilometer top. Anyway, that's a resource that could be used for gravity wave studies.
I see Hanli's got his hand raised.
Yes, I related to the discussion on the high-res, maybe regional refinement, and also the 3% John mentioned earlier. I was wondering if it's indeed 3% and with a 2-degree, current 2-degree 2.5 by 1.9 model, that would be 3% of that would be roughly 0.37 by on that order, 0.4 probably. So if we go to that resolution or a little bit lower, maybe quarter degree, will that solve the problem, or you really need to go to convective resolving?
The 5%, 3%, we're referring to a 1-degree simulation.
Oh, 1 degree. I see. Okay. So then it would be, it would be smaller. But I was wondering if I can take a quick calculation, but will that be, let's see, if it's 1 degree, that would be 0.17 degree, 3% would be that. Or we really need to go to the, this means that if we go to a 1/8 of a degree, we'll be able to probably resolving that. But maybe if you're not resolving the convection itself, maybe it's not sufficient.
Yeah, I agree with that last sentence. Yeah, thank you.
Hanli, I'll just make a point that the heating rates in the ZM convection scheme are governed by CAPE. And CAPE is set by well, it's a complicated function of boundary layer stuff, but it's primarily set by the large scale. And so the heating rates in ZM scheme are fairly insensitive to resolution. And so that's an argument for keeping that area fraction constant when you go from 2 degree to 1 degree, because the heating rates aren't going to be very different between 2 degree and 1 degree.
And that's also true if you go to even higher resolutions like quarter or 1/8.
I mean, unless somebody, that's the null hypothesis. Again, CAPE is very much governed by the large scale dynamics, and so less sensitive to resolution.
I see. Oh, thanks.
It would be nice to hear from the WACCM community their thoughts on the current vertical resolution, having a raising CAM to 80 or whatever. If anyone has any strong opinions on that, it'd be good to hear them.
Okay, since nobody seems to want to say anything about it, I think vertical resolution, if you want the QEO, you need at least 500 meters, lower stratosphere through about 10 hectopascals. And we can, obviously WACCM cannot have a top at 80 kilometers. So in that context, we are talking about the workhorse model. And we can build a real WACCM on top of that. But the workhorse model with a top at 80 kilometers, I think the main thing is to make sure that CGD does not taper resolution to something like 6 kilometers at the top. We should render the stratosphere useless even in the workhorse model. So something of the order of 3 kilometers will be much better. That entails about 10 extra levels in the overall scheme of things, which is about a 10% increase in cost. So I think that's the main thing we need to emphasize with CSM and CGD.
What about the role of WACCM in providing chemical fields for the CMAP simulations?
Presumably, the workhorse model will do that, right?
So you got to worry about a boundary condition and about transport and everything.
You do have to worry about that, and they haven't thought about it, and neither have I. But definitely, you have to worry about a boundary condition at 80 kilometers, which is going to be harder than a boundary condition at 140, where we have it now. I mean, you know, we didn't pick 140 just for the heck of it. There were good reasons for that.
But you don't invest. So you're saying that you don't think WACCM will have a role in the next simulation in generating chemical fields, radiative fields?
Well, you know, essentially, the argument has been for a long time now that why are we doing double simulations? You know, one with CAM for tuning up, and then WACCM for providing the chemical boundary conditions, and presumably that was one of the ideas about the workhorse model, to have something that could do everything at once. Right, and so that's where we are with that. I don't think you can sell a CESM on more than 90 to 100 vertical levels, and that will be a big stretch for them as it is. You know, having full WACCM will, with that kind of resolution, well, yeah, you will end up with quite a number of additional levels, plus all of the physics about 80 kilometers, which especially non-LTE radiative transfer, and having to keep track of energy of chemical products and so on. I don't think CGD wants to get involved in that. So yeah, that's how I see that going. But I mean, I see highlights over there. Maybe she has something to comment on it.
Yeah, well, I more wanted to ask what would we need to do then to figure out these boundary conditions? Is it just a case of running with the settings that are currently there and seeing if it looks reasonable, or are there kind of theoretical arguments for what needs to be done?
Well, I mean, if you're setting fluxes or concentrations of nitric oxide at 80 kilometers, they've got to come from somewhere, right? And you need a time-dependent upper boundary condition. So at some point, whether you go, okay, we're just going to stick with CMIP6 WACCM runs to provide an upper boundary condition for CMIP7, or how are you going to worry about long-lived tracers that end up, you know, at the high latitudes going through, you know, that you won't be able to get the full evolution of full transport of those long-lived tracers, the CFCs and those sort of things. So you're going to have to take a boundary condition from somewhere, I think. And hope that the fluxes coming down at high latitudes are reasonable.
Okay, and so if the next WACCM's chemistry behaves very differently, there would be motivation for generating new boundary conditions, or if it's similar, then maybe it's fine to just use the CMIP6 ones.
I mean, we're currently, you know, part of that NOx source is coming from energetic particles, which are being revised all the time in terms of what they think the fluxes are of those and how they're being generated. So, you know, there's no guarantee that they're not going to come up with a better specification for the solar forcing that might affect the composition above 80 kilometers.
Okay. Yeah, I think Rolando's right that that's definitely one of the motivations for making one model was to just run one for the CMIP activities.
Yeah, and it's also that we don't have to produce all the different variables for the CAM model anymore that were done before, obviously. So it's much less processing and more consistency doing that.
All right, well, it's 11, which I think is probably the tentative time we were supposed to wrap up. Does anyone else have anything to discuss at the last minute here? Because if not, we can adjourn for a lunch break. We actually don't restart up here until 1 p.m. But we do have a longer session this afternoon from 1 to 4. So in the interest of making sure everyone can make it through the day without getting too blown away by the schedule, I would advocate for ending the discussion now, going on our 2-hour lunch break, coming back at 1. Sound good to everyone?
Sounds like a good idea to me.
Thanks.
Conley's
right.
got his hand up. Is that-
Oh, sorry, I didn't see that. Hunley, your hand's still up if you wanted to say anything.
Oh, sorry. No, I'm
Okay.
ready to go.
Okay, all right, your hand's up to say, let's get out of here.
He's waving, yeah.
Yeah. Cool.
Bye.
Okay, everyone,
Bye.
see you in a couple hours.
All right. Christiana?
Yeah, it's 3 o'clock. I think we are still gaining a few people.
Okay.
So our first speaker of the session is Jiang Zhu from NCAR. We invited him to give the presentation, and it will shed light on the climate sensitivity from a paleoclimate perspective. So Jiang Zhu, take it away.
Thank you. Do you see the slide okay?
Yes.
Okay. First, I want to thank Julio for the invitation. And this talk is about assessing the equilibrium climate sensitivity of CESM2 using the last glacial maximum. So I'm Jiang Zhu, a project scientist here at NCAR from the paleoclimate group. So many of you may know that CESM2 has an ECS higher than 5. So the red dot here is much larger than previous CESM models, and it's larger than the consensus range in different assessment reports. Thanks to many papers, now we have a clear idea that the increase of climate sensitivity from CESM1 to CESM2 can be attributed to the stronger cloud feedback, but it's less clear whether this high ECS is realistic. So recently, there's an interesting paper suggesting that the high ECS is plausible. That's because in CAM-6 in CESM2, we corrected a mean state bias in CAM-5, and that should remove negative cloud phase feedback. Therefore, we should expect a stronger cloud feedback and a higher ECS. Because ECS is an important metric, so we need to carefully examine this through multiple lines of evidence. For example, we can use the reconstructions of the last glacial maximum to inform the ECS in the models. You can see that for major releases of CESM model, we do have LGM simulation, and they more or less fall within the proxy suggested range in terms of the global cooling. And in a recent paper, we refined the LGM global cooling to be around 6 degrees C. And we have good reason to rule out these lower estimates of the LGM global cooling. Next, let's perform CESM2 LGM simulation and compare the response against proxy data here. So I used the CMIP6 configuration, try my best to use the same configuration as close as possible, including the horizontal resolution, but still there are some differences. Those are not found to impact the pre-industrial climate as well as the ECS. For details, please check out my GRL paper. And for the LGM simulation, we used lower greenhouse gases and the presence of land ice sheets. Importantly, we used the pre-industrial aerosol and vegetation because global reconstructions are not available. And even if we have some constraint for those two and we incorporate those into the model, we have good reason to believe that they will make the simulation colder. And the CESM2 LGM simulation was initialized from CESM1. So here is a result on time series of the LGM global cooling in the model compared with proxy, so the black line with uncertainty range. The red is that the global cooling in CESM2. You'll see that after initialization, the model quickly drifted away, reaching an LGM global cooling more than 11 degrees C after 500 years. So this is certainly too cold than proxy, and it's almost impossible to reconcile with the uncertainty in proxy data and boundary condition. The orange simulation is the same as the red, except that I used the CAM-5 physics. Now you see that we have a realistic global cooling for the LGM and agrees better with proxy and agrees better with the solution in CESM1. That's the blue. So this exercise basically suggests that CAM-6 is the reason for this excessive cooling in CESM2. To further understand that, I performed a forcing feedback analysis. So this lambda here is the climate feedback parameter. Basically, you divide the climate radiative forcing by the temperature response. So you can compare this metric across different simulations. You see that the value in CESM2 is more positive than that in CESM1 by 0.4. What is causing this? The next column shows the shortwave cloud feedback. You see that the CESM2 value is also larger by 0.4. So this suggests that the cloud feedback explains 100% of the excessive LGM cooling in CESM2. That is consistent with findings that cloud feedback is responsible for the higher ECS in CESM2. So their connection can be very clearly seen. This column shows the shortwave cloud feedback in abrupt 4 times CO2 simulation. You see that globally the value is more positive in CESM2 by 0.4. And this close connection can also be seen in the zonal mean. Top panel in LGM simulations, bottom panel in abrupt 4 times CO2 simulations. You see that compared to CESM1, the blue line here, the CESM2 shortwave cloud feedback is more positive over the subtropics and the Southern Ocean. You basically see an overall similar feature in the abrupt 4 times CO2 simulation. So far I have shown you that the CESM2 LGM is too cold than proxy data, and its ECS is likely too high, and it's caused by the cloud feedback. Next, you may wonder why we have this so strong a cloud feedback. This figure is from Gettleman 2019. So they did a comprehensive examination of the differences between CAM5 and CAM6. And they pointed out that the shallow convection turbulence and the macrophysics and ice nucleation schemes, they all contributed to the higher cloud feedback in CESM2 CAM6. Next, I adopted this Gettleman approach in a fully coupled LGM configuration. The hope is that we can use the real-world data from the LGM, trying to provide some information about the different cloud schemes. So again, I'm showing time series of the LGM global cooling. I have 100-year here. The red is standard CESM2 CAM6 simulation. You see that it will be too cold than proxy data. And the orange is the same as the red, except that I use the old version of the ice nucleation scheme, so Myers 92. You see that this configuration produces a realistic LGM global cooling. And the green is the same as the red, except that I use the MG1 version of the macrophysics instead of MG2. This configuration can also give you this realistic LGM global cooling. The blue is I turn off CLAP, instead use the UW shallow convection scheme. It has overall limited impact on the temperature response to the LGM radiative forcing, shown in blue here. And the purple is I use the alternative way to calculate the autoconversion and accretion. So we have a large top of atmosphere imbalance at the end of the simulation. So if we extend the simulation longer, it will be still too cold. So what's the implication on ECS? Here, for each configuration, I performed slab ocean simulation to calculate the ECS, which are listed here. And you see that for each configuration that gives you this realistic LGM global cooling, the ECS is also much lower than that in the standard CAM6 simulation. By the way, those are in the FV2 configuration. So again, the connection between ECS and LGM simulation is through the cloud feedback. So here, x-axis is the LGM cloud feedback, the y-axis is WCO2 cloud feedback. So in slab ocean configuration, you'll notice this really nice correlation between the two. Of course, there will always be state dependence, meaning that the cloud feedback in warming simulations is stronger than that in cooling simulations. But this state dependence is overall small, and they tend to vary less across different configurations. So overall, they are not important here. So here is a closer look at the shortwave cloud feedback. We have a lot of lines here, but the main message is listed here. So zonal mean cloud feedback, black is CAM-5, red is CAM-6, and the orange is when you use the old ice nucleation scheme. You see that basically you revert the cloud feedback back to the CAM-5 level over the Southern Ocean. And if you use MG1, you basically revert the cloud feedback over the subtropics back to the CAM-5 level. And here are some further details regarding the cloud feedback in this head freeze off. So you use the old ice nucleation scheme. So I used offline radiation calculation to decompose the cloud feedback into water content, phase, amount, particle size, and the residue. This is standard CAM-6, and the red figure shows the difference. So you use the old ice nucleation scheme, you have more negative cloud feedback over the Southern Ocean, and that's largely attributed to the water content feedback. So you do have some contribution from cloud phase. Therefore, our hypothesis to explain the role of head freeze off is that compared to CAM-6, this configuration produces more ice nucleation particles, more cloud ice, and a stronger negative cloud lifetime feedback. Therefore, we have smaller LGM cooling and a smaller ECS. Regarding the MG1 off simulation, I don't have any new results on that, but I guess it has to do with the tuning of the KK2000 scheme and also the prognostic precipitation. So here is a summary. The LGM is too cold in CESM2. It suggests that the ECS is likely too high. The connection is through cloud feedback. And this paleoclimate simulation seems to suggest that there might be something problematic with the macrophysics, ice nucleation, or maybe it could be compensating error from other scheme. And I want to emphasize here is that it's relatively easier to perform a paleoclimate simulation and to point out that there might be something problematic in the model. It's much more challenging to do it correctly because a correct configuration should simulate past extreme cold and warm climates, should simulate present day observation, including the historical warming, and should also agree with process level understanding. That's why we need to examine multiple lines of evidence carefully. With that, thank you for your attention, and I'm happy to take questions.
Many thanks. Julio had a question. Julio, do you want to speak up?
Hi, Zhang. Thank you. That was very interesting. I just wanted to clarify that when you swap MG2, when you replace MG2 with MG1, do you also do you get het freeze off sort of as part of that package?
If I understand this correctly, when you use MG1 in CAM-6 configuration, you can also use the new ice nucleation scheme.
Okay, so you're
actually, I don't know that it will pick it up.
Okay,
I have to go look at that. They're brought in through a different set of variables, and so if in the default, you probably have. You'd have to find out if you turned het freeze off manually with MG1, you would get it, but if you didn't, you might get something even worse because you might have also removed Myers as well, which would be no mixed phase ice nucleation.
Okay, so it is possible that by doing MG1, you might just be redoing head freeze off.
Yes, that is true.
Okay.
Okay, thank you. Could you stop sharing your screen, Joe? Then we can move on to Kevin. So our next speaker is Kevin Reed from Stony Brook University.
All right, so can you see my screen?
Yes.
Okay, great. So shifting focuses a little bit, I was going to talk a little bit about some work that we're doing with an application of using the community atmosphere model. So this is a little bit different talk for AMWG, but I'm trying to highlight some of the tools and capabilities that we've been building in collaboration with folks in the university community to kind of use CAM for event attribution capabilities. And so this is some work that I've done with Michael Weiner, as well as Alyssa Stansfield, who'll be talking next, and some of her PhD work, as well as Colin Zarzicki at Penn State. And so the motivation here is that, you know, in any given year, we have numerous billion-dollar disasters in the United States. This trend has been growing. And if you look at this plot here, you'll notice that most of these disasters come in the eastern United States, and they're often related to kind of, you know, hydrometeorology extremes related to extreme weather, tropical cyclones, and flooding. And so one of the questions that we've been asking is that, can we actually explore the impact of climate change on rainfall associated with individual hurricanes? And can this be quantified using CAM and kind of these hindcast approaches, which I'll introduce in a second? And you know, can these frameworks actually then be utilized to actually translate the impacts of climate change in a way that's more conducive to policymakers and decision makers? And so, you know, the traditional approach to looking at how extreme weather changes in the future is to actually kind of run CAM as what it was meant to be ran as, right? So a long-term decadal simulations. And so, you know, typically you run, you know, 30, 40 year, in this case, AMIP simulations, and you at high resolution. So that's one of the differences here. We are using a global 25-kilometer grid. And we can track storms in these large climate data sets, and we can look at how these storms change. And the traditional way of doing this is built on some work that Alyssa has done as part of her PhD, which is to run a REF simulation, which is for the historical record from 1985 to 2015, to run under future time slice experiments into the future under RCP 4.5 and 8.5, and to look at things like, well, how do the general statistics of tropical cyclones change? And so so this plot just shows us that as you go into further down the plot, you're going from current climate to 4.5 and 8.5. These are the last 30 years of the 21st century. And you can see that this suggests that there's a decrease in the number of storms in the future. If you look at RX 5-day, this is just a metric for extreme precipitation. You can see that in the future, the model predicts that there's maybe a decrease in the amount of extreme precipitation that comes from tropical cyclones, but that's convoluted by the fact that there's been a decrease projected in tropical cyclones in the future. And so if you look at what we call this scaled RX 5-day, this is this ratio of the middle row to the left row, you can actually see that the model does project that in the future that the amount of rainfall per hour of storm impact is actually increasing pretty significantly. And this is the traditional way in which we've used CAM to explore extremes. And so some of the work that we've been trying to do is, well, can we build other ways that allows us to do this for high impact events and allows us to work in a way which is maybe more conducive to decision making? And so as just a note, similar here, we're using CAM5 in part because that's just what we've historically been using for tropical cyclone related simulations. We're using a variable resolution mesh with the high resolution domain over our area of interest. So we're using the SE dicor with an area over most of the North Atlantic as well as Eastern United States. And we're actually starting to treat CAM as a forecast model now, as opposed to a climate model. And what I mean by that is we're actually running very similar experiments to AMIP, except we're now initializing at specific times in advance of a hurricane landfall. And then in order to, unfortunately, we're not using DART at the moment for our data assimilation. We're actually just outsourcing our data assimilation by taking the initial conditions that have been assimilated for the NOAA GFS, doing a little bit of interpolation to our grid and some initial kind of spin up and we just run our 7-day forecast no different than you would a global forecast system. But in addition, because we are using a climate model, we have the ability to run what we call a counterfactual forecast. And this is a forecast in which everything is the same as the initial CAM forecast, which was actually developed a few years back by Zarzycki and Jablonowski. And we're actually now adjusting the initial conditions to remove the temperature, specific humidity, and SST climate footprints. And all that means is that actually we've run either CAM-5 as part of the C20C plus detection and attribution framework, or even using the CESM large ensemble, we can actually calculate differences in the large scale thermodynamic fields from the 1800 or 1850 control run versus a given time period that you're focused on. And so this is in essence the footprint of climate change to date, and we can remove that from our initial conditions. And this allows us to kind of maybe do a comparison of these two forecasts to say, can we actually start to use this type of framework to quantify the impact of climate change on an individual storm? And so just an update on our methodology, and this is, again, some of the work that Alyssa has developed, and she will be probably using this framework in her talk coming up next. But what we're doing here is when we do these ensemble simulations, we are going through and we're identifying tropical cyclone locations. We're stitching them together in trajectories to create something like this. So this is an example for Hurricane Florence, and this is some work that was published about a year ago, in which we actually just initialized the forecast on September 11th at 0Z using, again, the NOAA GFS initial conditions. And we run CAM as a 7-day forecast, both in this red actual and the blue counterfactual forecasts. And so we track them in time using tempest extremes. And what you can see here is that there's very little difference in in the track of the two forecasts. And this is great because this means that actually we can do an apples to apples comparison of the simulations to explore if there's an impact on the storm. Of course, a couple things to note, the track isn't perfect, and any global forecast system this far out in advance, multiple days before landfall, is not going to be perfect in the track. And so it's actually comparable to what other global systems have done. But it does capture important characteristics of the storm, like the slowdown that occurs near the landfall location. So this means that the model is somewhat fit for purpose for at least a comparison. And so the next thing we want to do is explore rainfall in these simulations. So the first thing we do is we extract the radial profile of the lower wind field to determine an outer size metric, which we take to be the radius of 8 meters per second. And then once we have that, we can, at every point in the storm, we can extract all of the rainfall associated with the tropical cyclone by using that outer radius as a definition of the size of the storm. And then this allows us to make plots like this. And so the left is the observed. This is the rainfall that actually occurred in Hurricane Florence in 2018. The middle is the actual forecast. So this is our best replication of trying to predict what we see on the left. But be clear here that this is a 98-member ensemble forecast. And so, of course, you can see some of the differences here in the location of the maximum rainfall, and that's due to slight differences in the storm location at landfall, as well as where the storm went after landfall. And as well, it's been smoothed out because it's 98 ensemble. It's a 98-member ensemble mean. But if you look at the counterfactual forecast all the way on the right, you can see that here from the ensemble mean, it's very clear that the precipitation has actually decreased in the 1850 counterfactual, meaning that that climate change has actually increased the amount of rainfall in Hurricane Florence. But we can do, obviously, a much more sophisticated analysis. So we can look at what is the point maximum inside this region, this blue region here that had the most amount of rainfall over the multiple days in which Hurricane Florence impacted the coast. And so you can see that in observations, the maximum amount of rainfall that occurred in a given region was about 33 inches. And the red plot here is the distribution of the 98 ensemble members and maximum accumulated amount at any given location that occurred. And you can see that actually the model does a really good job at simulating the extreme amount of rainfall. And if you compare it to the counterfactual, there's actually a shift. The counterfactual has about 4% less maximum accumulated rainfall. Another way to look at this would be to look at the total core rainfall. So this is kind of all the rainfall that occurs in the region. And so here you can see, okay, the model isn't as good at capturing the observed amount. But you can see, if anything here, there's a very clear shift that climate change has actually increased the total core rainfall within the storm by about 5%. And so this was kind of one of our first cases of doing this. And since we've started to build out and refine this methodology. And so here's just an example that we've done for Hurricane Dorian in 2019, which in some cases dumped almost a meter of rainfall in the Bahamas, in part because it did a very similar thing to Florence and Harvey, in which it slowed down over the region, over a given area when it was making landfall. But now we're looking at it from a different perspective. Instead of looking at the accumulated rainfall rates, we look at, okay, how likely is this vertical bar here? This is the maximum 3-hour rate from observations using the NASA eMERGE product. And what we look at is the likelihood that the actual or counterfactual produces a rate of that extremity. And what you see is that, well, of course, both models can produce, both forecasts produce simulations that have rain rates that higher than observations, but they're very rare, right? So these are 99.9 percentile events, but there's about a 16% increase in the likelihood of the maximum observed rate in the counterfactual, in the actual, simulation compared to the counterfactual. And so what this allows us to do is to build this out so we can start to do these things in relatively near time. So this is just an example for Hurricane Laura from this past year, in which we put out a statement on our website within about 24 hours of Hurricane Laura making landfall, doing a very similar analysis showing that Hurricane Laura's maximum rainfall was increased by about 10%. Due to climate change. And we've actually started to develop this to do it as kind of seasonal attribution approach, in which instead of initializing individual ensemble members at specific times in advance of storms locations when they're making landfall, we just initialize we've just essentially turned CAM into an operational forecast system, and we just initialize simulations every 3 days, starting at the beginning of the storm season all the way through the end. And then we can go back and analyze all storms in the simulations. And we can see that there's a very clear increase in rainfall in 2020 due to climate change. And you can look at this again in some of these more advanced metrics. And what you see, if you look at the mean maximum accumulated rainfall amount in any of these individual ensemble simulations throughout the entire season, we see about a 10% increase in the rates. And so what we're seeing is that the hindcast attribution frameworks demonstrate that climate change has increased rainfall rates and accumulated amounts in individual recent storms. And this is consistent with the traditional way in which we use CAM to project future changes using kind of time slice decadal experiments into the future. However, this event attribution framework does actually help to make the science more relatable to the public, as well as communicate it, but also practical for more climate adaptation strategies. And so just to finish, this is part of a growing effort in the scientific community to refine the application of attribution frameworks for the quantification of the impact of climate change on extreme events. One of the additional things that we started to do is to flip this around from, instead of being an attribution framework, to flip it around by using the CESM large ensemble to come up with fingerprints of what the world will be after an additional 1 or 2 or 3 degrees of warming. And so we could see of how would the 2020 season be different in a world in which it was 1 degree warmer than it is now, if we maybe reach the Paris Agreement, or if we go beyond that, how different would the storm be, the season be? And so I just want to acknowledge our funding sources, Department of Energy, NASA, as well as the Stony Brook Foundation for this work. And hopefully I have time for maybe a question or two. Thank you.
Thanks, Kevin. Julio had a question in the chat. And Peter Caldwell, so speak up, please.
Okay, yeah. Hi, Kevin. That was great. My question is about the pretty common projections from so many climate models that Atlantic hurricanes will decrease in warmer climates. Are we getting any sense of whether that's true or not?
Well, I'm not sure if we're getting any sense that that's true or not. I think that it's becoming less and less of a consensus as more models have started to suggest that maybe there isn't a decrease in the future in their projections. There seems to be a very big trade-off between the thermodynamic environment becoming more conducive to storms, but the precursor, the events that lead to storms, to cyclogenesis, the number of those is going to actually ultimately determine the number of storms in the future. And that is actually happening at scales that are typically not even well resolved, even in high resolution climate models. So I think, if anything, I think it's become a little bit murkier in the last few years.
Okay, but you're thinking that this what seemed to be a consensus a few years ago is sort of falling apart because models are, they must be improving in some way. Is that because they have higher resolution, or is it?
So yeah, I think it could be higher resolution. I think it's also it's related to necessarily maybe what goes on at the relatively small scales that leads to those precursor events, right? Those are the scales which are heavily influenced by, for example, divergence damping in the model. And you can actually tune the number of precursors you get very easily by toggling that switch, or even in the convection scheme. And so these are things that are often tuned out of the model, in part because it makes it harder to tune them. And it seems that these things actually are these really small scale features are probably really important for determining the number. And so if you're not getting those right for the necessarily right reasons, and maybe when you do the climate change projections, the impact on those precursors, that kind of small scale variability is less certain. And so I think it's just an acknowledgement that maybe some of our earlier high resolution models were maybe overly diffuse.
Okay, thanks. That's
so we are a little bit over, but there was, I think this is a perfect segue for Peter Colquitt's question. Peter, do you want to ask?
Yeah, so as a model developer, when I see these attribution studies, I often think, okay, well, that's true for the model world, but is that actually true for the real world? And so do you have any reaction to that in terms of, do you think that the numbers that you're quoting are real world numbers versus CAM biases?
Well, yeah, I mean, I think that there's always a little bit of uncertainty there, in the sense that, well, we can use the 1850 model simulation to compare against, right? And so our footprint is obviously in the model world. But I want to acknowledge that the footprint that we put into the model for these calculations is heavily conservative, because it's averaged over the 40 model ensemble members, for example, of the CESM large ensemble. And so what I have always thoroughly believed is that these analysis of 5% for some of these storms is probably an extremely conservative estimate, and that the likelihood is it's probably actually larger. And so that doesn't quite get, so that doesn't quite answer your question, but and in the end, I don't have a footprint to remove from 1850 because we don't have global gridded data in 1850, right? And so this is just one of the tools that we can use to inform decisions, right? So this is a way of developing a scientific methodology that is trying to answer a question that the public is asking, as well as stakeholders are asking. And so, like most things, I'll turn it around and say, projections that we build these climate models to do into the future, right? There will never happen, right? There will never be a correct forecast of 2100, but it's still worthwhile to do these things because these are the best tools that we have to try to quantify future impacts. And so I would say it's the same perspective from the attribution side of things.
So I think we do need to move on, Kevin. Thanks a lot. And the next speaker is Alyssa Stansfield, and she's continuing the discussion about tropical cyclones.
Yeah, thank you so much. Okay, hold on.
And she's from Stony Brook, I should add.
Yes, so I am from Stony Brook. Kevin's my advisor. So yeah, we're continuing the TC theme here. And actually, I was just thinking that hopefully my work in the future will be able to shine a little light on if what we're seeing in the model world is kind of comparable to observations, but I'll get to that at the end of my presentation. So yeah, I'm looking at how tropical cyclone precipitation changes in response to idealized warming in some of these simpler CAM aquaplanet simulations. And so just as a brief introduction, we know that from the IPCC reports and multiple studies within, that we expect the frequency and intensity of heavy precipitation events to increase in the future. And the leading theory behind why precipitation increases is the Clausius-Clapeyron relationship, which basically says that for every 1 degree Celsius warming in the atmosphere, the air can hold about 7% more water vapor. And so we expect the heavy precipitation to kind of scale with that increase in water vapor. However, there is some observational evidence that in the tropics, heavy precipitation increases may exceed the Clausius-Clapeyron scaling. And so what about tropical cyclones? You know, have been many modeling studies that project tropical cyclone precipitation to increase as well, but by how much exactly is kind of uncertain. We saw the estimates from Kevin's work. There's also just many different ways to estimate this. You can look at 2-day spatial averages. You can average over different radii around the storm and estimate the precipitation change. Or you can look at a specific region like the Eastern United States, like I did and my colleagues in this paper in 2020 that Kevin also mentioned in the beginning of his talk. And so it's a little tough because you kind of get different numbers depending on what metric you're looking at, what ocean basin you're looking at. And so what I hope to do with my work is utilize radiative convective equilibrium, or RCE, simulations to better understand how interactions between the thermodynamics and the dynamic processes within TCs increase their precipitation with climate change. And so I kind of want to try to narrow these numbers down a little bit more for TCs. And just as a refresh, so radiative convective equilibrium is just an idealization of the tropical atmosphere where radiative cooling and convective heating are in statistical balance. And so why do I want to use RCE? So basically there's no land in these simulations. The sea surface temperature is the same everywhere. And there's no kind of like general circulation, so no wind shear. And so basically there's nothing that can like kill TCs like in the real world. And so this allows our sole focus to be on the tropical cyclones and not their interactions with complex environments. And so just to show you kind of what these simulations look like, there's many different types of RCE simulations. There's a good overview in this paper, Merlis and Held 2019. And the one I'll be using is this one in this purple box, where we have, a spherical Earth that's rotating, and it just has the same SST and solar insolation everywhere. And so tropical cyclones are kind of allowed to travel wherever they want to on the globe. I'll talk a little bit more about that later, what this exactly looks like. So yeah, I'm using CAM-5. I'm using CESM2 with the official RCEMIP comp set, which Levi Silvers talked a little bit about in his presentation yesterday. And so I'm using the protocols of RCEMIP, which are described in Wing et al. 2018, except that I'm adding rotation. And so if you look at this schematic down here, the idea is we kind of want to simplify down from the real Earth. You can look at AMIP type simulations, which are the typical simulations used in these studies, like I showed in my third slide. Then we go to RCEMIP type simulations where the resolution is around 100 kilometers. The SST is the same everywhere. The solar insolation is the same everywhere. There's no seasonal or diurnal cycles. And then all the way on the right is kind of what my simulations look like. So we increase the horizontal grid spacing to about 28 kilometers. I'm using the SE dynamical core, and I'm adding rotation. And so I run 11 simulations with uniform sea surface temperature, varying from 295 to 305 Kelvin in 1 Kelvin increments. And so just to give you an example of what these simulations look like, on the left here is an animation of wind speed on the 300 Kelvin simulation. And so all of these little dots you see rotating are tropical cyclones. I'll just note that they are tracked using the Tempest Extreme software, which is available on GitHub that Kevin also mentioned. And so what we see is that these storms tend to form in the tropics and subtropics, move westward and poleward, and kind of accumulate up near the poles. And so this isn't new. These simulations have been done before to look at different things, such as in Shavas and Reed 2019. They looked at the dynamical impacts on a storm size and where storms generate in these simulations. And what they found is that basically these TC worlds, as they're called, are split up into an equatorial belt where there's other equatorial waves, the TCs tend to form. And then there's the polar cap, which you can see here, where the TCs kind of accumulate up and they sometimes interact with each other, sometimes just die out. And so just to look at some characteristics of the TCs in this world, on the left is a plot of the distributions of the lifetime maximum intensities of the TCs. So just to remind you, these numbers and the colors represent the different SSTs of the simulations. And so what we see here is that you can see these markers on the x-axis. This is the medians of this distribution. So as we would expect, the median intensity increases as the sea surface temperature increases. And the maximum lifetime maximum intensity also increases as the SST increases, which is in line with the Carey-Emanuel's potential intensity theory. We expect to see more intense storms as the SST increases. I'll also note that, especially for the kind of warmer half of these simulations, these distributions tend to be bimodal, and this is actually what's seen in observation. So that's kind of interesting that we see that characteristic. And so this plot on the right just shows some global and time mean global and time mean characteristics. So these green diamonds are the global and time mean number of storms. On the x-axis is the SST. So we see that the global and time mean number of storms decreases as the SST increases. If you look at the orange circles, the average outer size increases as the SST increases. And then to kind of see which of these characteristics kind of went out, I calculated the percentage of the globe that's covered by TCs, which is the triangles, and we see that that slightly decreases as the SST increases. So basically, on average, as the SST increases, we see more intense storms and larger storms. And so to get into precipitation, on the left here is a distributions of the frequency of different precipitation rates. So the x-axis is precipitation rates on a log scale. And what we see is that as the SST warms, there's a shift away from smaller precipitation rates and a shift towards more extreme precipitation rates, which you can see here on this extreme right tail. So the warmer simulations have more frequent extreme precipitation rates and larger precipitation rates. And on the right is the same x-axis precipitation rate, but this is showing the amount of precipitation in millimeters per day that comes from each precipitation rate. And so we see that similarly as the SST increases, the amount of precipitation that's coming from these really extreme precipitation rates in the TCs increases. And so this plot shows, this is a bit of a big plot here, so I kind of describe what it is, but just looking at the main plot in these colors, this shows the joint dependence of the maximum TC precipitation, which is the colored boxes, on the SST, which is the y-axis, and the TC intensity, which is the x-axis. And so each of these boxes, these colored boxes, is the median of a distribution of thousands of tropical cyclones at each SST and TC intensity combination. And so what this shows, a really basic result this shows, is that as the TC intensity and SST increase, the maximum TC precipitation increases as well, which is what we would expect. And then these side figures here, these line plots, show the mean percentage change in precipitation calculated across each column or each row. And so this is showing the percentage change in precipitation per intensity change. This one on the bottom is showing the percentage change in precipitation per SST change. And so generally we see that these percentage changes are positive. This one kind of aligns with the Clausius-Clapeyron rate of 7%. This is kind of a new plot here, so we're still teasing out like what exactly we can see from this plot. But yeah, the basic result that is encouraging is that we see that in these RC simulations, TC precipitation increases with increasing SST and TC intensity. And so just to go over my preliminary results and what I'm doing now. So in these CAM-RC simulations, warmer sea surface temperatures leads to less tropical cyclones at any one time, more intense and larger TCs on average, more extreme TC precipitation rates, and more of this precipitation is coming from those extreme rates. And so what I'm working on now is kind of trying to understand how much of these precipitation increases comes from the thermodynamic impact of warming, which is an increase in specific humidity, versus dynamic changes we see. So increases in TC intensity and size. And we're trying to split up that effect to see how much of the TC precipitation increases comes from either one. And so looking a little more into the future, what I eventually want to do is evaluate how well these results from the RC simulations can translate to more realistic GCM simulations. So I want to go from my rotating RC EMIP simulations back to how does it compare to AMIP simulations, and then possibly how does it compare to observations. And so results from this 2017 paper suggest that TC structure in RC simulations, AMIP simulations, and observations are consistent. So, that's a good sign that hopefully we can get some information about precipitation from the RCE simulations and apply it to AMIP and real world. And so one way that I'm considering doing this is kind of using this joint dependence plot. So this plot all the way on the right is the one piece of the one I just showed you 2 slides ago. This one in the middle is one from an AMIP simulation that I had. And so we see that they're matching up pretty well. And then all the way on the left, I want to try to make the same thing for different observational data sets and kind of see how that compares to these RC MIP simulations. And so that's my plan, to eventually kind of see how these can apply to the real world. Yeah, so that's all I had. Thank you for listening, and I'd be happy to take any questions.
Thanks, Alyssa. We have a few questions here in the chat. Zhao Ning, do you want to start?
Sure. Hi. There are lots of pretty cool results. I was just wondering on slide 8, there seemed to be, when you were showing the changes in the TC statistics with regard to the change with SC, I just find it really intriguing that they seem almost linear. So this, with the understanding that there's probably not a simple theory for TCs, but I was just curious if there would be any scaling arguments and whether this relationship is the same or different with regard to the equatorial and the polar regimes that you have shown the division with for the dominant length scale.
Yeah, so yeah, it is interesting that it ends up being linear. I think one thing that I'm definitely curious about in that regard is looking at the number of TCs, because that kind of relates back to this question that a lot of people have, is how does the TC number change with climate change? Maybe this could give some insight into that. Why does the number of storms on this planet decrease as the SST increases? I think that's a really good question to look into. As far as why the outer size is like this, there's like not too many theories on size that we have right now, so it's kind of hard to say. But yeah, I think that's a really interesting question. There's definitely a lot you can look into with these simulations that I just haven't had the chance. And as far as like splitting it up into the polar region versus the equatorial region, we've been doing that. And yeah, the trends we see are kind of the same. I didn't get to show it here, but in the equatorial region, actually the TC sizes tend to be actually the same between the simulations, and where we see the size change the most is in that polar cap. And so we're still kind of try to tease out like how that relates to the real world, because obviously in the real world we don't have TCs accumulating near the poles. So yeah,
cool.
Thank you.
Yeah, and we basically have a 25-minute discussion period. So there are 2 more questions, Alyssa, for you, but I also want to open it up to the other questions that appeared in the chat that were related to climate sensitivity. So maybe we go still with Alyssa, and Peter Caldwell and Thomas had questions. Maybe Peter first.
Yeah, I just had the quick question of whether you've checked about whether the strong precip increases the increases in strong precipitation that you're seeing are matching the Clausius-Clapeyron around 7% per K rate.
Yeah, so I see that's kind of what we're like working on now and looking at the thermodynamic versus dynamic effect, because there's kind of like a lot of different ways you can calculate it. And so I think what we're seeing here is that generally it is in line, but it kind of depends on how you look at it. And so I think that breaking up the effects into the thermodynamic versus dynamic impacts will kind of help us answer that question a little bit more. But I'd say generally, yes.
Okay, thanks.
So Thomas, is your question answered? You mentioned something in the chat.
Oh, well, yes, partially, I could say. I wanted to ask a similar question also to Kevin. Namely, I'm still curious about I don't know why my camera is not working, sorry. Curious about the distinguishing purely thermodynamic effects on storm development and growth and dissipation, and the effects of the circulation they're embedded in. And this is potentially an issue both for the counterfactual forecasts and for this funny world forecasts, where the circulation must be very different from what we have in the real world. So the storm tracks are pretty much unconstrained, probably. They can go wherever they like, and maybe they bump into each other from time to time and merge or destroy each other. So could that have impacts both on the number of storms and on their size and on their precipitation amounts? And if so, what else could we do in order to maybe evaluate that impact?
Yeah, so that's a great question. I definitely think the storm interactions near the poles do have some sort of effect, probably like, as you say, on the lifetime, so that would affect the count. And so what we've been doing is actually kind of trying to split the analysis up into the pole versus the kind of equatorial belt, and kind of, assume that the equatorial belt is more analogous to what you would see in the real tropics, which I think is a pretty fair assumption, minus the land. And so we have been, for the precipitation analysis, we actually have been limiting it to just the equatorial belt, which I didn't mention in my presentation, but those figures are limited. Yeah, just to try to avoid those effects of the interactions. I think you also had directed this kind of at Kevin, so I don't know if you wanted to add anything.
Yeah, so maybe I'll just add one quick thing. So, for the hindcast ones that we're doing in these kind of attribution approaches, we do not, as you bring up a good point, Thomas, and that we do not actually alter the dynamical fields. And that's by design, because we're trying to get simulations that are comparable. And if you updated the dynamical fields based upon the kind of climate footprint, then the tracks of the storms could be very different, which makes it difficult to then compare them.
Right. Yes.
But it's worth mentioning, actually, though, that while these storms in the simulations that Alyssa has shown are kind of, you're right, they can kind of just go wherever, that the process in which they form and by genesis and then migrate poleward is actually very realistic, because that's actually what storms do in the reality. Of course, now their mechanisms might be coming from different formation regions, because we don't have African easterly waves. Maybe some of the other precursors are a little bit different, but the real advantage of that approach is actually that by trying to understand what controls the size and genesis in this idealized world, has actually started to really inform the way we actually understand what sets genesis rates in reality. Because when you kind of get this world that has this only tropical cyclones, what we've discovered is that what's often referred to in the literature for what controls tropical cyclone size is this inverse F scaling. So this idea, right, is that you can only pile so many storms on, and so if they're spinning faster, they'll be smaller, but you'll have more storms potentially. But what we've actually discovered is what actually controls the genesis rate and the length scale in the tropics is actually an inverse beta scale. So this is kind of the Rhine scaling, which is, oceanographers would say, oh, we talk about the Rhine scaling all the time. But this is something that by using these really idealized frameworks, we've kind of stumbled onto, in part because it just forces us to look at things in a different way. And now other folks at GFDL have taken those length scales and turned them into genesis rates, and it can actually explain the differences in their future climate runs, in part by looking at differences in the scaling of the Rhine scale and in the future simulations and the precursors. And so there's, of course, there's always this trade-off between this is just such a realistic thing that what can we really learn from it? But I think this is the value that CAM provides to the community that most global climate or global atmospheric models do not, is that it offers this ability to kind of do these weird things with the model, which actually can really, really advance our understanding in science. It can be great for model development, but it seems to actually be really nice tools to kind of sit back and think about what controls these things from a very simple view, and then see if it migrates back up into the more realistic simulations.
Yeah, I second that. So we are big supporters, Kevin and I, of the simpler model framework, which is a great accomplishment of CSM. I suggest we, just as a heads up, how we organize this discussion period, we have another session at 2:15 Mountain Time, and everybody probably deserves at least a 5-minute break. So I suggest we spend maybe 4 or 5 more minutes until 2 p.m. on the tropical cyclone topic. And there was a very active discussion in the chat also about the climate sensitivity, which we can return to it in 5 minutes or so.
So Brian, I want to, can I address these kind of, I think, somewhat related questions that Brian and Rich.
Yeah, Brian, and I just wanted to mention Brian's question. Yes.
Well, maybe, I don't know if one of you, well.
So Brian, do you want to unmute?
I didn't really want to, but I was just wondering about the division between the dynamic and the thermodynamic. We usually think of the thermodynamic contribution as being this just Clausius Clapeyron, so you get more moisture, so you get more rain. But there's also these microphysical effects, and there's also cloud radiative effects that I'm not going to bring up right now. But in terms of microphysics, if you change the structure, the stability of the troposphere, you raise the freezing level, you change the buoyancy within the storms, and you can also change the process rates in the microphysics that could change the intensity of the storms and the precipitation efficiency. So I was just wondering if you've thought very much about how that's going to affect the precipitation associated with tropical cyclones.
Yeah, so that's a good question. So we're probably pretty early in the process of just trying to break it down by some basic thermodynamics versus dynamics. But I think that you're right that there's a variety of ways in which the thermodynamics could potentially impact it, in part through the stability potentially of the atmosphere, which is another thing that could be included. So we've been trying to think about different ways in which we can kind of do a decomposition into the different components to try to come up with a way to explain the percent difference. And so I think maybe we'll have to ask you some more questions about if you have a good idea of maybe how to do that to potentially look at the terms. But I think for tropical cyclones, I think that there's going to be I guess my intuition suggests that there's kind of some dominant players, and I think that the near surface specific humidity is going to be one of the most dominant. But of course, but I think the effects that you're talking about could actually feed back onto the dynamic side even more, right? And so that's where I think that would be really worth trying to figure out how to work that in.
Yeah, I think looking at the atmospheric stability is definitely something we should do at some point. But this is great to get this feedback from people who know the model so much better than I do.
So related to Rich's question. So Rich asked about this breakdown between the large scale and convective precip in the warming simulations. So we haven't, I don't think, directly looked at that in this work. But I think that, you know, if I remember incorrectly, Angie Pendergrass has looked at this in some of the future simulations within CESM large ensemble and does see a couple, well, she sees some nonlinearity in the precipitation change, which I think is maybe related to a change in the partitioning between the large scale and the convective parameterization in terms of where the precip is coming from. And one thing that's always been interesting to me, and this will be crazy to throw out right when we're supposed to be done, is that I've often noticed that, and this going back to some of the work that Adam has done a few years ago, is that precipitation changes in the future in conventional CAM can sometimes look different to the precipitation changes you see when you just go from low to high resolution. And meaning that there's some interesting nonlinearities that happen in both cases that I think comes in part from that shift in the convection of basically the convection doing less and less. And so the large scale is doing more in both cases, in a warming world in these simulations, as well as in going to high resolution. And I think that's probably something worth figuring out a good way maybe with a group of us to study within CAM, because that could really be biasing projections of precipitation.
Yeah, I mean, yeah, you got it exactly right. I mean, I've always thought about, you know, in terms of Clausius-Clapeyron and stability, you know, both the large scale and the convective respond very differently to local versus non-local stability changes, and it's always I've always been interested to understand how that would occur in reference to increases in temperature.
But yeah, that could be in these idealized simulations, Alyssa, we should make a note, because that could be something we could look at pretty quickly, the breakdown between convective and total precip.
So I would like to come back also to climate sensitivity, and I know there were chat questions. So please unmute yourself and let's swing over into this discussion.
Well, I'm just going to say, you know, it's not really about climate sensitivity per se, but I just was also struck by this session, and maybe agreeing with Kevin, that, you know, it really illustrates kind of the poles, the poles that we need to, you know, we need to cover when we're looking at climate change. And it sort of, I think it really brings home the sort of the wide range of things that CAM has to do. You know, we need to, CSM/CAM needs to do the projections, which probably have to continue at you know, relatively low resolution coupled, but we also have to look at high resolution studies to, you know, understand the dynamics of what's going on in the mesoscale and looking at idealized configurations. You know, I'm really struck by what Kevin said, that, you know, the thinking on what's controlling the frequency of storms in these high resolution climate models is changing. I think that's, well, that's very interesting. But anyway, I just think it really kind of brings home, you know, what kind of a big problem we have. And that's all.
So I wondered whether paleoclimate studies are part of the typical testing portfolio when a model is released. And this is maybe a question for AMP and also Jiangsu.
Yeah, I think in terms of LGM, it's challenging to do. So we spend, I think, years on this. And the simulation took a long time to reach equilibrium. And you need the sea ice over the Southern Ocean to build up slowly to give you this correct ocean circulation. So for us, we took a shortcut. We initialized the model from available CSM1 LGM. But overall, the point is that it's challenging to perform those simulations. I guess that's part of the reasons people don't do that frequently.
And can you remind me, was that a 2 degree or 1 degree
I
assessment?
tried both resolutions.
Did it matter?
The 2 degree has a higher ECS if you calculate that using slab ocean. So that's 6.1 degrees C versus around 5.5 or 6 in slab ocean. So the LGM is also colder in 2 degree.
And that part of that is due to tuning changes between 2 degree and 1 degree.
Yeah.
It's interesting because WACCM has the same sensitivity also in slab simulations at 2 degree and 1 degree. We tuned different parameters, in fact, to get the 2 degree to behave. So that it could be interesting to compare that.
So is there some consensus or opinion in the community whether those high sensitivities are realistic? You know, you would suggest they're not, or they might not be with paleoclimate studies, but what's the consensus or what's the discussion in the community?
I would only speak from a paleoclimate perspective. In the past, we also used the CESM2 to simulate warm climate, like the Pliocene and Eocene. In general, the amount of warming you get in the simulation is also larger than the proxy data.
So Jean, didn't Steve Sherwood though suggest a range kind of high end of 4.5 to 5 in his review paper?
I believe the high end doesn't go that high, maybe around 4. I may be wrong.
It'll be interesting to see what IPCC comes out with. I kind of know, but I'm not going to quote it.
And there's that paper by Trudy Strolmo, right? Where she says the high climate sensitivity is reasonable. I'm hoping someone else that knows more will chime in, but that's as much as I can repeat.
My feeling is that the high climate sensitivities above 5 are viewed with more skepticism than if they were below 4.5.
That's my impression as well. I know recent work from GFDL has pointed out that the models with high sensitivity often struggle to get the historical record right. And so I think that they lay out a reasonable argument for thinking that those are probably overestimates without being too positive.
Yeah. CSM is kind of unique in actually getting the 20th century correct among the high sensitivity models. And I would agree with what Brian said.
HabGem 3 is doing an LGM now, and they have a high climate sensitivity. So once they have gotten the simulation a little bit longer, we're going to talk to them more. And what Christiane asked, we probably should use somehow paleo in our development, but as Jean said, it's hard. So it'd be good to brainstorm how we could do this within a reasonable development cycle and a reasonable time.
So I think one thing that's interesting in Zhang's presentation, which I think is a new plot that I hadn't seen before, is he showed the feedback differences in the LGM by latitude in some of the different simulations. And what's noticeable is that what you see is that the positive feedback in CAM-6 in the LGM moves into the tropics and the subtropics more, which is totally consistent if you think about it. It's just because if you're, we think of it extending to higher latitudes if it's a phase feedback. Well, the phase feedback is going to extend to lower latitudes in colder climates. And that's interesting because it may actually be displacing the low cloud feedbacks that are occurring now and in the future in those latitudes. And that's an interesting conundrum, which is a whole different balance of the cloud feedbacks than we've seen in the other simulations, which is also to say, it's not, especially the work that Mark Zelinka has shown is compelling to me, that I'm not arguing with the fact that the sensitivities above 5 are pretty hard to justify. I totally get that. And especially the LGM results are some of the best things that show that. So I'm not defending per se the values with CAM-6, but we know those feedbacks at high latitudes look better with respect to the present day and the process rates. And what Mark Zelink has pointed out is that we're probably overcooking the shallow cloud feedbacks. And so we may actually need to look elsewhere than just the high latitudes for correcting this issue. And what Zhang is showing is that in the LGM, it actually is extending into those subtropical latitudes because of the way that the clouds are shifting. And the balance of feedbacks and regimes is actually somewhat different. So I thought that was pretty interesting and something we have to think a little more about.
So it's 2:10. This line is open. So I guess we end officially the discussion, but of course we have 5 more minutes for those who want to talk more. We reconvene the next session in 5 minutes. So please feel free to stay on the line or step away for a few minutes, and we meet in 5 minutes.
Brian, it would be funnier if you had actual popcorn in real life, in addition to your picture for when you're not on camera.
Oh man, we have a popcorn. We even have those like red and white popcorn holders. Should go grab one of those.
You could really mess with everybody out here.
Actually, Brian, I think you should put up the white cat. Have you seen the white cat?
Yeah.
No, what's the white cat?
God.
Oh yeah, the lawyer in Texas. Yeah.
That's just the best.
I haven't seen that.
Oh, just Google Texas lawyer white cat.
Yeah, it's hilarious.
It is the best thing I've seen in a long time.
I love that he has to say, "I'm not a cat."
Yeah, I'm not a cat. Yeah.
I'm not a cat.
Is that like an Instagram filter, or can you do that in Zoom?
I guess.
It's a Zoom filter, I think.
Okay.
There's definitely filters in Zoom. I haven't looked for the cat, but
I can't find the cat.
Oh, you got a filter. Party hat, or is that pizza?
nice. From that special hair tonic.
Oh, I see now that we're still streaming on YouTube.
Oh, you're trending, Brian. I just looked. Yeah, actually,
I'm well known as an influencer.
Oh yeah, I'll ask a serious question. So Kevin, I mean, when you look at the structure of the tropical cyclones, have you ever kind of decomposed the tendencies from different processes to say where they change if you do a kind of circular symmetric breakdown of the particular tropical cyclone?
So
where the heating comes from more convection or more large scale, and where it is in the vertical.
So we haven't done this directly with these idealized simulations. There's some work out of Dae-Hoon Kim's group at Washington with Newman that had done some of this, where they kind of looked at radial profiles of like latent heat flux and sensible heat flux and things like that.
Right.
But I think what you're asking is even a little bit more, right? Actually looking
I'm asking about vertical
tendencies,
profiles.
And looking at kind of profile at almost a 2D plot as a function of radial.
Exactly. Yeah. I mean, you need a high frequency, obviously, data to do that in the vertical, but I think that's really
I mean, that's where the idealized simulations would actually be useful, because one of the things that we didn't mention, but is that, as Alyssa mentioned, that they're called TC worlds for a reason, because they just produce a large number of storms, which means you have a lot of statistics you can do with only running a 1 or 2 year simulation, as opposed to having to run a 30 or 40 year AMIP simulation to get the same number of tropical cyclones. Of course, the trade-off is they're just a little bit, maybe not quite as, it's not the same realism, but I think that's probably something that could definitely be explored.
Mm-hmm. Yeah, that'd be fun.
But when you go across these temperature ranges, it's not as straightforward as you would like it to be, as everybody would expect. I mean, we're trying to just diagnose percentage differences using composites, and it's pretty, sometimes they just, there's always this weird case when you go from one temperature to another where it just does something different than all the other temperatures when you look at it from kind of a composite standpoint. And it's always a little frustrating, but that's why they call it science, right?
As you increase the temperature, do you see the same thing that we saw with non-rotating RCE in Angie's paper, where you see these like abrupt transitions?
So it's a little bit more continuous, and so they're not as abrupt. And I think that's because you've, to some extent, in the paper without rotation, you kind of go from an aggregated to an unaggregated to an aggregated state, where in the TC world, you are always just in some kind of form of an aggregated state. So I think it's just less abrupt.
So I think we should actually continue the next session with the next session. And the next speaker is Peter Caldwell from Lawrence Livermore National Lab.
Okay, let's see how this goes. Can you see my screen?
Yes, perfect.
Great. Okay, so I'm going to talk about a different model than CAM. I'm going to talk about this model called SCREAM, which is E3SM's global cloud resolving model, so focused at 3 kilometers resolution. And this is an effort that I'm leading. It's why I haven't been doing much in AMWG in the last 2.5 years. There's about 20 people involved in the project. Nobody's working full time. And you can see this picture in the upper right from back when you could do such things as actually meet in person. And so SCREAM stands for the Simple Cloud Resolving E3SM Atmosphere Model. And I think that the simple bit is maybe the part that I'm most fond of. I think that it's really a good idea to keep code as simple as possible, because you shouldn't trust results that you don't understand physically. And the simplicity is also really great because, as I'll show you later, we're rewriting the code from scratch in C++, and we need it to be simple in order to make that tractable. And the fact that we're trying to run at 3 kilometers globally also adds to the simplicity, because you don't need as complicated parameterizations if you're actually resolving things. And so the cloud resolving bit is not really accurate in that we're running at 3 kilometer horizontal resolution, 128 layers in the vertical, top at 40 kilometers. So this means we're more, we have higher vertical resolution than I think most models. We have about 50 meter resolution in the boundary layer. But I just couldn't resist the acronym SCREAM. So we're cloud resolving, and we're trying to eventually run at higher resolution as well. So we'll grow into the name. So SCREAM is now planned to be the only E3SM atmosphere model in V4. So this will be a split from it being kind of a CAM-like model right now. And our ultimate goal is to run coupled simulations, which we haven't tried yet, but maybe by Monday we will have. It's something we're working on right now. And so why 3 kilometer resolution? I'd really like to run at 50 meter resolution, but we can't afford it. And so it's kind of a compromise. I think that 3 kilometers is tractable, and it's also where you start to resolve the largest of deep convective events explicitly. And that's really important because we all know deep convection is something that's a real struggle to parameterize. And also, at least before everyone jumped on the CMIP6 bandwagon of thinking that it's the mixed phase clouds that are important for climate sensitivity, we thought that deep convection was the important thing. And so there's something really important that you should understand with these global cloud resolving models that are becoming all the rage right now, is that so they play really well with GPU machines, and the increasing parallelism that we're getting instead of faster clock speeds these days. You can parallelize more columns trivially, but when you go to higher resolution, you have to take shorter time steps for CFL stability. And so that means that in order to run the same, say 10 years, you end up taking something like 10 times more time steps. And so these simulations are going to be short, like a year-ish for the foreseeable future. And so it's kind of a weird thing to have a climate model that you can only run for a year. And so you have to think about what you can do. And I think that this is actually a reasonable situation because as others have alluded to in today, clouds are the main source of climate uncertainty. And we also know that clouds respond on the order of a couple of days to forcing changes. And so you can get pretty far with cleverly designed tests. And so CES experiments, which are being shown in this right-hand plot, are one way that you could do this. Nudging to observations with a perturbed simulation for like aerosol sensitivity studies or something. It's also something that's been done to good effect. And so I think that an important science frontier is how can we be clever to get information out of these high resolution models. So specifically, what is in SCREAM? So the fluid dynamics is going to be a non-hydrostatic version of the spectral element approach that's in CESM these days. Radiation is going to be the next generation of the RTMG parameterization. It's also in CESM. Microphysics is going to be something that we started with the predicted particle properties or P3 scheme, and we've been making modifications lately to make it play nicely with the shock, turbulence, and cloud parameterization. You can think of shock as being kind of a lightweight version of CLUB. It's very similar in terms of the PDF that it uses and diagnosing, in this case, higher order moments. And then we're using prescribed aerosols for right now, but there's actually an even bigger project than SCREAM that is focused on creating a prognostic aerosol scheme for us. And then just as a novelty, I'll point out that we are using the PhysGrid paradigm. So our grid for doing the physics parameterizations is coarser than doing the dynamics. And so in terms of the implementation, we're doing this in two phases. The first phase is actually just implementing our parameterizations into the existing E3SM/CESM framework, so in Fortran. And so we can't run on GPUs in this framework, but we did that because it serves as a template for the C++ porting that we're doing, and that it's easier to communicate code than ideas. And we're also using it right now for scientific exploration. So I'm excited to get to that part of the talk where I show you results. And then the second phase is to do the C++ implementation. We're using a library called Cocos that is a C++ library. It's one of the reasons why we're running in C++. And that basically abstracts the performance, the parallelism that you need in order to be able to run a single code base on CPU and GPU, and hopefully whatever comes next. And so this has been quite successful already for the die core, which is complete. And we are able to do a 3-kilometer global simulation using the NGGPS benchmark, achieving 1 simulated year per day using about all of the Summit machine. And so this is 3 times faster than anyone's been able to do before, and will hopefully allow us to do some really cool simulations. So, okay, and so one more slide on V1. This is just showing an example of the code. So the original Fortran, I think this is for calculating the fall velocity of cloud water in Fortran at the top, and then C++ on the bottom. And the punchline here is that there's more code needed for the C++ version than for the Fortran version. This is partly just a result of it being C++, but it's also the result of needing to be more specific in order to unlock more parallelism. So I think this is going to result in SCREAM being probably harder to use for someone that doesn't spend a lot of time doing computer science. And so this isn't a pathway that I would propose for a community model, but E3SM is supposed to be focused on computer science. And so I thought that it was an interesting thing to try. So this is a sociological experiment. If I'm out of a job in a couple of years, you'll know that it was a bad idea. And so moving on to talking about the Scream version 0, so this Fortran version, we have recently done a 40-day simulation at 3 kilometers, and we are in the process of uploading it to the Diamond intercomparison. And so this is a global intercomparison of global cloud resolving models. We're currently in the second phase of it. So there was an initial phase where they simulated 40 days starting in August of 2016. That first phase of Diamond is done. There's some papers on it. And so now there's phase 2. And so there's a link if you want to look at that. And so there's, for this phase 2, people are doing coupled simulations, but you can also do a fixed SST simulation. So that's what we're going to submit. And so the output from all of the Diamond simulations is going to be available from the link that I've posted at. But if you want, let me know, and you can have access to our data on NERSC as well, so you don't have to download it. And so we really, I can't stress that we did not have time to tune or polish our run at all, but I was kind of shocked at how well it turned out. And so this graphic on the right-hand side is just showing the global average values. Each dot is a different day of the 40-day simulation. And the reference is going to be observational values. These are anomalies on the y-axis, so the dots should all be centered. The black dots are all centered on 0, and then Scream are different days in blue. And so you can see that we're something like 5 to 10 watts per meter squared out of balance for the short wave and the long wave, but that cancels in the net. And the latent heat flux is a little bit unfortunate, but on the whole, things look pretty good. And it looks pretty good compared to other Diamond simulations as far as we can tell. So that's great. In terms of top of atmosphere radiative balance, the kind of punchlines are that we basically don't have enough clouds everywhere, and we're working on how to tune that. The stratocumulus regions look pretty good compared to most GCMs, so it makes us happy. And in general, there's not enough tropical deep convective clouds. So we can make pretty pictures. That might be the main use of this model. And so we're able to get stratocumulus off of the coast of South America. And it looks pretty good. In terms of precipitation in general looks great. In particular, the diurnal cycle on the left-hand side here. We're getting the phase speed for MJO propagation correct, but the frequency is too high. And so we seem to have kind of this popcorn cumulus problem that is something that we think we know how to tune away, but we couldn't do it in time. So just in terms of the punchline, so the Scream version 0 is running. You can use the model. You can grab the data from the intercomparison. There's a lot of room for improvement, but there's also a lot that is doing well. In particular, spending my career working on a GCM, now working on a cloud resolving model, I'm really amazed at how many problems go away when you move to finer grid spacing, even before you do any tuning. So that's interesting. And then Scream version 1 is going to be available this summer. And I think that we're probably going to get something like 0.5 simulated years per day. So this is going to be, I think, great. So that's it.
Thanks, Peter. If you have a question, I don't see any chat question, but
hey,
please
Peter, can I
unmute
sorry,
yourself.
Oh, yeah. So Peter, I noticed it was 1 simulated year per day on the whole of the summit. Is that right?
Yeah, that's right.
And that was Fortran GPU enabled or not?
It's C++.
Okay. Okay. So that figure you quoted was for the C++ version.
Yeah. So the die core is already done, already ported to C++.
So do you where is the speed up going to come from then? I guess is the
You mean, so if the die-core is running at 1 simulated year per day,
Yeah.
how do we get the whole model to run at 0.5 simulated years per day?
Well, I get, but that's on the whole machine.
Yeah.
Okay.
I guess, so I think if we can use all of Summit, which is probably unrealistic, we can get something like 0.5 simulated years per day.
But what's, I guess, so your quote of 0.5 simulated years per day, how much of a kind of the machine would that ultimately be hoped to be? Over like 20% of the machine to run half a CPU?
Yeah, I mean, so I think we'll see what the actual throughput is, but the basic calculation is that it's using all of Summit. Basically, we can get 0.5 simulated years per day. So I think we can speed up the die core a lot because we're not using semi-Lagrangian advection yet.
Okay.
Once that's done, then we'll be faster, but then we have to add the physics, and the physics is going to slow it down again. So.
Okay.
So we only have time for maybe one more question. Megan, maybe go ahead, and Adam, please, could you type your question into the chat for Peter?
Thank you. Very interesting presentation. Thank you so much. So I was wondering, for porting to GPUs, why were you converting the Fortran code to C++ and then port it to GPU? Why not use Fortran CUDA to basically reduce one extra step of rewriting the code in C++?
Yeah, so the issue that we've seen is with Fortran CUDA that there's things like the order in memory that you want to have. You need to change for your GPUs versus for your CPUs, and you end up having code that looks really branchy and or you have a different version of your code that you're using on GPUs than on CPUs. And so Cocos hides all of that. And so you have more of just a single code version you can use for everything for CPUs and GPUs. But Cocos is a C++ abstract. So that's why.
Thank you. So Peter, please stop sharing your screen.
Sorry about that. If I can figure out how. There we go.
And we move on to the next speaker, and that's Garrett Limon from the University of Michigan, talking about a machine learning project.
Okay. Hello, everyone. Can you see and hear okay?
Yes.
Okay. Yeah, so thanks for the introduction, Christiana. My name is Garrett Limon, and I'm going to talk a little bit about some of the work Christiana and I actually do at the University of Michigan on some machine learning techniques as emulators for simple physics in CAM. And here we go. So some of the overarching questions on this work is basically, can the machine learning methods be used in this way? I think some of us probably already have seen some papers that suggest that it can in different in the context of different questions, but also how well does it work? Is it physically realistic? Is it within appropriate dynamic ranges? And do these techniques offer any improvements in computational efficiency and performance? And something that we look at internally, because it's kind of a tricky task to train machine learning models, is how do the performance of these models depend on data selection, preparation, the technique, the architecture, and the hyperparameter choices. And thankfully, we've been using a tool called Sherpa that's helped a lot with the hyperparameter part of this. And then lastly, we are starting to look into enforcing physical constraints and physics aware types of machine learning, because we do have a lot of physical knowledge and we want to make sure we're utilizing it. So we do this in our work in a hierarchy step, kind of like how you would build a GCM. So we don't go straight into the full physics climate models, but we start here with a 3D dynamical core and the dry and moist versions of the Held-Suarez test, which I hope a lot of you have already heard about, so I don't spend too much time here. But yeah, the dry test is essentially utilizing some Rayleigh friction at the top of the atmosphere for the velocity field and a temperature relaxation for the temperature field. And the reason this is useful is because we know that such a linear function is capable of being replaced with something like linear regression, particularly for the U field. But for T, linear regression is just not quite able to capture it completely. There's a little bit of nonlinearity that is there that it kind of allows us to start playing around with machine learning in order to capture it. And so we're looking mostly at this temperature tendency here for the dry, and also in the moist case when things get a lot more complicated on the right-hand side. So we add a lot of different forcings for boundary layer, heat fluxes and other things, and we get a lot more nonlinearity, even though it's still a very simple problem. We also look at machine learning for predicting precipitation rates in these models and see how those work as well. So just a little background on machine learning. You have some inputs that relate to some outputs, and you want to determine what the functional relationship is. Of course, we know the functional relationship, but we want to know if a machine learning model can come up with this same relationship in the context of its algorithm. You usually will feed in a whole lot of data into some algorithm, which I'm labeling here in this picture as a black box. And then you try to determine what gives you the appropriate output. It's a regression problem. And we're working for our black boxes, we're using neural networks and random forests, and we're using the open source workflows of Keras and scikit-learn to build them, which makes everything a lot easier for us in Python. And then some optimization is done with Sherpa, which I mentioned before, which is coming out of the University of the UC Irvine. And if anyone is thinking of using machine learning, I highly recommend looking into it, but it's not the only choice. Some quick just diagrams. I don't want to spend too much time here, but the random forest is an ensemble of decision trees. It's an algorithm that you create an instance, and then you pass the algorithm determines this or that types of questions that then lead to a prediction class, and then the final prediction is based on some average of the ensemble's prediction. I encourage you to look further into that. It's a little bit complicated, but also a very useful machine learning algorithm for a lot of different cases. Neural networks, I'm sure you've heard about, they're very popular. You essentially have a whole bunch of linear regression problems, y equals ax plus b, except you, instead of using a linear function, you're for each neuron here, you're applying a nonlinear activation to it, such as tangent or hyperbolic tangent function, sigmoid, and other more complicated ones. And this introduces a lot of nonlinearity, and you essentially have the sum of a whole bunch of weights and biases that determine this functional relationship between x's and your y's. And these are the two that we're utilizing at the moment. For our training data, or the work that we're doing, the data that we're generating from CAM, we're using the finite volume dynamical core at what we're calling 2 degree, but it's the 1.9 by 2.5 degree resolution. And we run it for about 60 years with weekly output. We're collecting all of these different variables. The red just means it's only available for the moist case. And then we split the data up, about 40 years for training, 10 years for validating, which is kind of grouped into the same thing down here. And then we leave about 4 years of a gap and 6 years to test on. That's in order to avoid overfitting and having too much autocorrelation between the signals. If we break down really quickly what the kind of data we're looking at is, we're feeding in, our samples are going to be columns. So we have 52 weeks of 50 years at this resolution. We end up with tens of millions of columns to work with, which is ideal for such machine learning tasks, because the more data, the better it is, the easier to come up with that functional relationship, although the longer it takes to train. So everything's done offline. We do some reshaping of the data, which I just kind of mentioned. We do some normalization to create unitarily invariant data. And here in data science, you just subtract the mean, divide by the standard deviation. And something that I actually have some runs going at the moment to look at is whether or not the means and standard deviations depend on the physics of the problem, because we know that we can do weighted means, we could do time only means, or we could do global means of the full sample space. And we in this work, we're doing global means of the full sample space with a weighting, but that might not be necessary, and we want to know if there's any impact there. So we're looking into that at the moment. And then we do shuffle this to avoid even more correlation between adjacent signals. So quickly going over the dry test, it shouldn't be surprising. Both of these machine learning models are able to capture the majority of the forcing because it's so simple. The difference plot here on the right, where you have the neural networks on the top and the random forest on the bottom, are all relatively close to zero. And here in the middle, you have the neural networks result. This is a time and zonal mean plot of the full testing field. And to just jump straight in the interest of time to the moist case, we see immediately that the random forest here on the bottom is capturing all the areas of interest quite well. The extreme heating in the mid latitudes that shows up here as just a little bit warmer in the average, and then also the equatorial region, whereas the neural network is struggling to do both. We've had runs that do really well in the equatorial region and then don't capture anything here. And then this run is one of my newer ones that was able to do a little bit of both, but struggles in as well. And we looked at the R squared of these signals as well. And this random forest here is doing surprisingly well. It's one of the best that we've seen both in our work and in literature. The closer to 1 basically means the better it is at identifying the signal and predicting or emulating the function. And then here the neural network is struggling significantly, but it does have a positive correlation in most of the field, although extremely low and nothing to be excited about at the moment. I do want to mention part of the reason that the random forest is so much better, I think, is because we were able to use Sherpa to tune every parameter that we wanted to, and the neural network, just due to computational constraints, we weren't able to use Sherpa for all of the parameters. So that could be that's something we're trying to work on as far as wall clock times when we run these. I'm going to go extremely quickly because I'm already out of time, but we've also looked at precipitation, and I'm just going to let this video play here on the right side, where you have a neural network predicting the precipitation rate on the bottom and the actual precipitation rate on the testing data on the top. And I do want to mention this is a different data set. This is only a 3-year data set at 3 hourly output, but otherwise same configuration, same model setup for that moist held Suarez. And we see that it does extremely well. Here on the right, we have a little time zonal mean plot of this. However, we do identify in just the time mean some significant negative precipitation, which we obviously don't want to find there. So it's capable for the precipitation rate, which is a pretty difficult problem because this is an integration of a 3D field, but it does come with some physical questionable physics that we want to make sure we tune out of that. And we're thinking about ways of how to tackle that problem. So I'll leave this summary slide here and end so we can get at least 1 or 2 questions in. And yeah, thank you.
Thanks, Garrett. I don't see any chat questions right now, so please speak up if you have one. Megan?
Hello. Sorry. Very interesting presentation. I have a quick question. Have you done any thoughts on how you want to implement this back into the Fortran code?
We have some ideas. We don't want to reinvent the wheel, and there are definitely different teams that have already begun tackling this problem. So when we're ready, which we want to figure out this neural network to kind of get it a little bit closer in line with the random forest, we do plan on reaching out to some groups that have tackled this problem for some guidance, but it seems like there are a few tools that are already out there that can take a Python trained model and turn it into a Fortran subroutine. So after that, it's mostly just on our side to couple that subroutine into the CAM. But yeah, we haven't begun that work yet. So
That's great.
Mhm.
So Colin raises a question. Colin, do you want to speak up?
So I read the question, Colin. I haven't done anything along the lines of things that Libby or Ema or a few of the other researchers in that field of making that black box a lot more transparent have done. But one thing that I did do is I've been playing around with that neural network, and certain choices that I've made have allowed the neural network to, like I kind of alluded to here in this result, which is one of my more recent from earlier this week, we see a little bit of the heating in the mid latitudes showing up with these bands. And if I had a snapshot, I'm sure you guys have seen most of this, but you really suffer in the equator. And in my prior results, which you may have seen at AMS, if anyone saw my talk there or my poster at AGU, was doing really well at the equatorial region and completely missing the heating bands in the mid latitudes. And these are just simple hyperparameter choices that are just clearly, like you said, identifying certain things in the data that might be easier to come up with versus other things. And there's a little bit of a trade-off. We want it to do well at both, which is the random forest seemingly able to do. But for some reason, so far, we haven't found the right neural network setup to do that.
And Andrew points out in the chat that there are a few successes at NCAR. I think
Yes.
Andrew has worked on that, and David Gagne. And there's also Vulcan.
Right. Yeah,
the
these
Vulcan
are
group, Chris Brotherton, who have demonstrated it's possible with the GFDL model.
exactly. Yeah, these are all parts of the groups that I had in mind as I answered quite a little bit vaguely there on the first question. But,
so there are a few groups, and even in the literature, it's documented now. It's nothing standard. Maybe that's a problem. Okay, thanks, Garrett. I think we do need to move on. Could you please stop sharing your screen?
Yes. Thanks, guys. How do I stop? Stop. Wait, oh, it says new share. Oh, pause? No.
There should be a button, stop sharing.
Why don't I see it? Okay, exit. Here, I see it. I'm sorry.
Okay.
I was looking for it and
you.
I made it harder to find. Okay, thanks, guys.
Thank you. So next talk is by Gunther Hübler from the University of Wisconsin-Milwaukee.
Hi, can everyone hear me?
Yes, can you share your screen?
Yes. Sorry, one second.
Gunther, did we lose you? Oh, there.
Oh, yeah, hello?
Yeah.
Oh, sorry, I muted myself again. Okay. Meeting looks broken. Okay, here we go. Okay, sorry about that.
Go ahead.
Okay, so hi, my name's Gunther, and I've been working with Dr. Vincent Larson at the University of Wisconsin-Milwaukee on a way to utilize GPUs for long-duration climate simulations. So the focus of this presentation will be about a recent project we've been working on that could provide a way to use many-core architecture-based supercomputers to do long-duration climate simulations. So by many-core architecture, I'm mainly referring to GPUs, since that seems to be the current big boom in how we're improving computational power, but this can also apply to many-core CPUs too, which are starting to become more and more common. So we're working on this because supercomputers with GPUs are becoming so popular, and they offer up a much greater amount of theoretical computational power. And of course, we want to use as much of that as possible. But the catch is that with so many GPUs and cores, running without highly parallel code would be just a waste of allocation time. So in order to utilize computational power, we need to provide the GPUs with a sufficient amount of work. And in order for this, in order to do science, we need that work to be useful. So there's a variable amount of parallelism in existing climate models already, and that parallelism being the ability to increase the resolution of the model without, or since the grid columns are mostly independent of each other, the large amount of the computations are. The issue with that, though, is that there's a trade-off between resolution and throughput. And to justify the use of GPUs, we would need roughly 3-kilometer grid spacing. And with newer GPUs, that would go even down. And that would require somewhere around a 15-second time step, resulting in less than 1 simulated year per day. But for long duration climate simulations, we're looking for more like at least 5 simulated years per day. So our proposal for solving this problem is to maintain coarse resolutions, but to improve the accuracy of existing models with the use of subcolumns. Now, these subcolumns would be used to perform physics calculations such as microphysics, radiation, or aerosols. And since subcolumn computations can be done completely in parallel, we're able to provide the GPUs with plenty of work by doing so. Now, the scientific purpose of subcolumns is to better estimate the effects of subgrid variability. So for a quick example, when a cloud parameterization outputs a cloud fraction for a certain grid box, that cloud is essentially being treated as being uniformly distributed across that grid box, when in reality that cloud fraction could have a high variability, meaning some parts of the cloud are dense and could cause rain, which is a pretty important effect to capture, while other parts of the grid box are just clear air, which would allow something like radiation to pass through to lower grid levels more. So the subcolumn method we're working on is called CESM, and it works by generating subcolumns from the most recent grid column data. So a PDF of fields are predicted at each grid level by a physics parameterization. And this vertically correlated set of samples is being treated as what a subcolumn is. So, we take a vertically correlated random set of samples, and this vertical set is a subcolumn. And so after generating all these subcolumns, we take those and we pass that into some kind of physics method, physics calculation, and average the results from that physics step, then assign that average back to the grid column. So CESM has already been implemented and tested in CAM, and this result shows climate simulation, but with differing number of subcolumns. And the figure plotted is the 5-year average of cloud brightness. So the first image is a run without subcolumns for reference. The second one is a run with 4 subcolumns and already shows a significantly better RMS error. The third image shows a run with 10 subcolumns and even better RMS error. And the fourth image shows a run with 50 subcolumns where the results differ slightly from the 10 subcolumn run. So from this, we can see that subcolumns do improve results, and the results are noticeably different in a 5-year average, even when using more than 10 subcolumns. Now, what makes this all parallelizable is the fact that subcolumns are completely independent of each other. And since we can change the number of subcolumns that are used per grid column, this level of parallelism is variable without affecting the time step. So to provide more parallel work, we can simply increase the number of subcolumns that are used. So in theory, this amount of parallel work can be adjusted to use GPUs fully. And we've seen that subcolumns improve results, making the extra GPU work useful for coarse resolution models. Now, the other aspect of this project we have to be concerned about is whether or not these types of computations are suitable to use GPUs efficiently. Because it would be easy to just crank up the number of subcolumns and fill up the GPUs. But if the performance is poor, then we simply can't do that. So the first thing to consider is that the vast majority of physical calculations are vertically and horizontally independent already. And that combined with subcolumns, which adds another level of parallelism, we have 3 levels of parallel work, which is pretty much the ideal amount for GPUs. And the only aspect of this pipeline that can't be done completely in parallel is this averaging step, where we take all the subcolumns and we average the results together from the physics calculation and then assign that back to the host model. But that's also the cheapest part. It's just a mostly simple average. Now, the thing that really makes this method shine, though, is that we don't need to copy this subcolumn data to and from the GPU. We're able to copy only the grid column data to the GPU, and then only the average data back off from the GPU. And that's really important because this data copy step is just about the biggest performance killer for GPU code. It's very expensive. So CILS is able to minimize data transfers by only needing to move the grid column data, effectively bypassing major bottlenecks due to slow data transfer speeds. And so now some of you may remember that I gave a similar presentation about our project last year, but at the time we only had CILS running on GPUs. So we went ahead and GPUized MG3 as well to develop a more complete prototype. And CILS is set up in a way that allows us to reuse that same code with any type of GPUized physics method. We would only need to integrate the model or integrate it into the model and work on the interface to ensure that the subcolumn data doesn't need to be copied to and from the GPU. So while the code isn't complete in a full stack sense, we have the biggest parts running, allowing us to do some meaningful timing tests and get a better sense of how performance scales. And that's exactly what we did. So the bulk of our testing was done on our workstation machines equipped with a P4000 GPU, which is getting kind of slow relative to new ones. And the runs were tested using a single Xeon CPU core. So this gives us a general sense of how the efficiency of GPUs and CPUs compares and changes as a function of the number of subcolumns used per grid column. So here we have plotted subcolumns per second, and it's as a function of subcolumns, which really subcolumns per grid column. So we can see that the GPU quickly surpasses the CPU in terms of how many subcolumns it's able to compute per second relative to a CPU core. And not only that, but the GPU continues to become more and more efficient as the number of subcolumns to generate increases. And I've run some tests into the thousands of subcolumns, and it continues to improve in efficiency while the CPU remains pretty much the constant level of how many subcolumns it can handle per second per core. And so here I've done the same type analysis with the GPUized version of MG3, and we see the same type of result. So the efficiency on CPUs remains roughly constant, while the efficiency on GPUs increases proportionally with the number of subcolumns per grid column. And the crossover point here is quite a bit more than it was for CILS alone, but there's still a lot of GPU optimizations that we can do to bring that down. Not to mention this was run on a relatively slow GPU, while the CPU core performance isn't too far off what modern CPU cores are capable of. So we can expect GPUs to embarrass the CPU even more. So from these estimates, we can't really say anything about how much extra work the subcolumn method will add. Instead, we've tried to break it down into parts and analyze their computational efficiency of each individually. And since the number of subcolumns per grid column can be varied, it can be changed to achieve either a certain accuracy improvement or just to run optimally on any future machine. So as GPUs become more powerful and available, the code running on GPUs will become cheaper, which will result in either increased throughput of the model or will allow us to increase the number of subcolumns to improve accuracy while maintaining existing throughput. So to summarize, we know subcolumns can be used to improve the accuracy of low resolution, long duration climate simulations. And that type of parallelism that they provide is flexible, allowing us to adjust the number of subcolumns to whatever runs best on current hardware or to a certain accuracy target. And as a proof of concepts and to get useful timing measurements, we built a prototype that calculates microphysics on subcolumns, but this method can be applied to other physics methods as well, such as aerosols and radiation, to provide even more highly parallel work to GPUs. And so far, the timing estimates appear to be promising, and there doesn't seem to be any major roadblocks ahead. So if you're interested in running climate models with subcolumns, please do get in touch with us. That's it.
Thanks, Gunther.
Yeah.
I don't see any chat questions. So if you have a question, please unmute yourself and speak up.
I have a question, which is that, so it seems like Thayer Calder's work was saying that the sweet spot is something like 16 subcolumns, but your analysis suggested, particularly for MG3, that you have to use more like 100 subcolumns or something to really see a benefit. So is that an issue, or do you think that there is value to using 100 subcolumns rather than 16? And do you see a pathway forward here?
Yeah, so it kind of depends on the number of columns we're running per node. So if we have, say, like 10 columns being calculated by a single CPU core, and then running 16 columns per grid column, that's something like 160 column or subcolumns essentially per CPU core. And the CPUs, there's a lot of cores per node. Or I think the newest supercomputer nodes are probably in the hundreds, whereas there's only 4 to 6 GPUs per those newer nodes. So you kind of have to multiply by the number of CPU cores and the number of subcolumns, or the number of columns being handled by each core, to get a better estimate for that. But yeah, we expect that number to go down quite significantly too. We haven't done much optimizations with the MG3 code yet.
So Rich Neal also has a question. Rich, do you want to?
I think mine's really the same as that. Yeah,
Okay,
just the possibility of putting a varying number of columns onto each GPU.
Sorry, I'm not trying to understand. Variable number of subcolumns on?
No, it's kind of the same question, really. Just the possibility of putting, based on how many subcolumns you do, and a varying number of columns onto a particular GPU, such that the net subcolumns might be well balanced.
Right.
Yeah.
Yeah, that's the hope, that we'll be able to get there. We don't have, a full stack set of code running yet, and we haven't had the chance to test on. We like to test on Casper, but we've been having some troubles getting that working. Yeah, hopefully we'll be able to get some more solid numbers in the future.
Thanks, Gunther. I think we should move on. Could you stop sharing your screen, please?
Sure. Wherever that is, pause share.
Yeah.
There we go.
Yeah, we still see your screen. So is there a button you can press? Stop sharing. Gunther?
I can't share yet.
Okay, perfect. Okay. So next speaker is Trude Eidhammer from NCAR.
Let's see. Can you see this?
Yes. Do you want to put it in presentation mode?
Yeah. Oh, I usually use PowerPoint, so where do I put it in presentation mode?
Upper right corner.
There.
Okay.
Upper right corner. Yeah, I can't. There you go.
View.
All the
well, there we go.
There. Okay.
Yes, perfect.
Okay. So I'm Trude Eidhammer, and I'm working closely with Andrew Gettleman and Kate Bayer-Calder and Hugh Morrison on producing a perturbed parameter ensemble for CAM-6. And the goal of this, so we call it PPE, and the goal of this is to understand the sensitivity of a large set of parameters in CAM-6 to changes in parameters. And this can also help us tune new parameterizations in CAM-6. And the method we're going to do is that instead of changing one parameter for each simulations, we are going to use something called Latin hypercube sampling. So we have developed a list of parameters, and we're going to pick out sets of these parameters. And we are going to have to run simulations like 3 to 5 times at least, more simulations than we have parameters. And I'm going to explain a little bit about the Latin hypercube sampling. And then we're going to run all the experiments, and then we're going to create emulators from the output. So we're going to also talk a little bit about that. And we have some CPU time to do this, and we hope to start soon to test with SCAM. And we're going to make all of the outputs available for the community so they can do their own testing, have science questions. And the intent is to modify the CAM physics, such as microphysics, the aerosols, deep convection, and club. So Latin hypercube sampling. As I said, we could run the model with a large set of parameters and just change each parameter one time, but that would be thousands and thousands of simulations. So we can make sets out of these parameters, and we could do it randomly, but we wouldn't be guaranteed to have the parameters going over the entire parameter space. So instead, we're using something called Latin hypercube sampling. So that first we have to decide how many sample points we want, and then so many simulations we want. And then this Latin hypercube set up for each simulations, set up a set of parameter. But it will remember what is set up before. So for next simulation, it will set up a different set of parameter, but make sure that it cover all the parameter space. So this is only like a 2-dimensional Latin sampling. But this is now, we're going to have over 20, 30 parameters. And this is how it looks like for a 5-dimensional parameter set. So you have, this is all the figures I'm showing. We haven't done anything else ourselves really yet. So these are taken from other papers, and I am citing the papers here. So this is with 5 parameters. You have 3, for the cube here, you have 3 different parameters. And you can see the spacing in between here, that it's cover the entire space, but also make sure that all the parameters are covered in the entire space. And then the colors here shows a different parameter. So you can see the colors are spread out in the entire box here, and all the circles here are different parameters too. So the sizes shows that. So this is for a distribution of 250 experiments that these people were conducting. And then what we do, we run all the simulations. We run 200, 400, 500 simulations, depending on how many parameters we're going to have. And then what we do is, what we want to look at is an output. We want to look at how the outputs are infected by the different parameters. So, for example, we want to know how the CCN concentration varies with the with changing parameters. So, what I show here is an example of emulation. So, what we do afterward is producing an emulation of this. So we take, for example, 5, we have parameter, this is, for example, the SO2 emission of, and this is now for this amount of SO2 emission, you get a certain amount of CCN. And so here we have 5 points. We have 5 parameters, perturbations, and then 5 outputs. And what we want to do then is to emulate this, actually creating function that we can randomly sample later on. So this is now an example of 600 different type of emulations to describe this curve. And all the parameters are actually an input for this function here. So the thickness of this emulation curve shows you the uncertainty in the emulation. But then what you can do then is take, for example, CCN again, and we can plot this as a 2-dimensional, and we can see for different parameters. We can see that, for example, the nucleation or the critical size of nucleation of the molecules does not have much impact at all on CCN concentration. But of course, SO2 emissions has a large impact. But we can do this for many different outputs, cloud forcing or whatever you want to look at, and then you can pick whatever parameter you want to look at the sensitivity. And another thing we can do with this is also to optimize the model and also tuning the model. So for example, here in A, that's a distribution of all possible CCN concentration that we got from all the different parameters sets. But then we can compare them with what is realistic. We have observations. So in C, you can see these are all the plausible CCN concentrations you can have in this region here. So now we know outside of here, all these parameter combinations are not valid or not plausible. So by doing that, we can actually reduce our set of parameters later on. And we can also maybe see that some of the parameters doesn't affect anything, and we don't even have to include this parameter test. And the same thing with forcings. I mean, if we know we can observe forcing, cloud forcing, and we look at observations, and then we can exclude all the parameter sets that is not realistic. So this is not the best screenshot, but we have a list of parameter, and we have parameter that we have put into name list and that we are going to work on. So it's their list here of club, MG3 pumas, aerosol, and then deep convection. And if you want to, I can send you this to you if you're interested. So, and also if you are interested in participating in this or having your favorite parameter looked at, you can let us know. We haven't started the simulations yet. And what we're going to do first is to run it with SCAM, and we hope to start soon. And then simulations will be on a 1-grid standard with CAM6, AMID, and or Nudge. So the goal we have with these simulations is to figure out how many different parameters, how they are sensitive, how the climate is sensitive to all these parameters. So we're going to look at the mean state climate and aerosol forcing and also cloud feedbacks. And we want to do this with minimal simulations. So for mean state, we are going to just only run a few years of F2000 climate or F historic climate. For aerosol forcing, we're going to then run 1 year nudged pre-industrial and then 2000 aerosols. And then for cloud feedbacks, we're just going to take the mean state and then add 4K sea surface temperature. And also the goal is to start with CAM and SCAM. And then when we do that, we can hopefully reduce the number of parameters that we're going to do then for the whole global simulations. And as said again, if anyone wants to add their own favorite parameters, that's easy to do. So the progress, we have created the Latin Hypercube code that creates the simulation sets and makes sure that all the parameters are distributed not evenly, but they over the entire parameter set, and we save them as netcdf file. And then we have CAM scripts that read in these netcdf files and then run all the simulations that with all the parameter sets we have in the netcdf files. The emulator code, I don't know if we have that yet ready, but that's the one that takes the output CAM output and it creates an emulator over the entire set. And with the emulator, we can sample randomly lots of model variants because of, so this is in 3 pieces, Latin Hypercube, CAM, run script, and emulator code. And again, yes, and with this, we hope we can also answer several different science questions. So, summary, PPE is a good way to probe the sensitivity of CAM6 physics. And we are developing this as a community tool for creation, run, and analysis step. Just gonna let this summary sit here, and then if anyone are interested in participating in this, or at least get the parameters in and create a name list for it if there's not even there yet there, you can contact Andrew Gettleman, or you can also contact me.
Thanks, Trude. So we have 2 chat questions. Let's start with Marcus.
Let me see if I can get to it.
I can also read it, or Marcus, do you want to speak up?
Yeah, hi Trudy, thanks for the talks, it's very nice. I'm wondering, are you planning on going with Gaussian processes like you showed with what the Leeds group has done, or something else like neural networks or polynomial chaos? And are you planning on comparing different emulator strategies?
I am not sure. Andrew Gettleman has been in contact with it, and I wonder if we might go with the Leeds group, actually. I am not quite sure on that step yet. Thanks for the question.
So, Rich?
Yeah, you talked about SCAM at first, but I worry, it depends what you look at, but I worry that if, for example, you want to look at the sensitivity of precip, you won't be able to do it because it's a constrained system. The surface moisture fluxes will be the same, I guess, for each simulation. So I'm wondering what you might be looking in SCAM, or different aspects, the time varying aspects, I don't know.
Yeah, cloud forcing. We haven't decided yet what exactly.
Okay, cloud is good, fine, yeah.
And but yeah, I'm glad. It's a good comment and something to keep in mind on if we suddenly decide to look at precip, and just remember that we can't do that in SCAM. So thanks.
Thanks, Trude. I think we should move on. Could you stop sharing the screen, please?
Yes, yep.
And our next speaker, and also last speaker of this session, is Roy Rasmussen from NCAR. We then have a discussion period afterwards. So Roy, take it away.
Okay. You're seeing my last slide first.
Yes.
Okay, well, I'd like to thank Julio for inviting me to give this talk. This grew out of a water cycle retreat we had back in January. And he asked me to talk a little bit about the water system, especially related to South America. So I thought I'd talk about the South America Affinity Group, which is a group of scientists that have formed from across NCAR and across the world. And given this pandemic situation, it actually helps because we have virtual meetings all the time. And it actually, I think, facilitates people joining. So everybody's used to virtual meetings. So this is a great way to connect. We have people from England and Europe and South America, of course, and from the United States. So lots of people interested in South America. So the motivation has been threefold. Number one, it's not very well studied in the past. Number two, global modeling, like a lot of the work that you guys are doing at CGD, obviously needs to capture some of these impacts of the ecosystems, mesoscale factors, and terrain that happens in South America, the Andes, the Amazon, Patagonia, MCSs, gravity waves, etc. And we eventually want to go to global modeling at high resolution. Convective permitting modeling is what we call it, less than 4 kilometers. So this is a great continent to test it on, and we're testing it with the exact same configuration of WRF that we've been testing in the continental US. And I'll get to that here in a second. So some of the topics that I think many of you are already aware of are listed here. Right this morning, we had a meeting where we looked at MCSs in La Plata and the Amazon. And I didn't realize this, but the La Plata MCSs are bigger and stronger than those in the Amazon. So any model that is going to simulate mesoscale convective systems has to be able to capture that difference. So the South America Affinity Group really started from a retreat we had of the water system program back in 2009. It was up at the Mesa Lab meeting room. And we've been meeting ever since then. We started with about 5 people, and now we're up to consistently over 30. So it has grown, and the group has been very active. Every meeting, we typically have a featured speaker talking about some of their research. And then we've established a website, which I've given here. And the PowerPoints from each meeting and the recordings are put on this website, so everybody can see and hear the meetings afterwards if they miss them or want to go back and listen to particular sections again. And one of the big things that we're doing is we're going to do a convective permitting simulation over the entire South America. And we've already started that, and I'll show you some results here in a second. And the group has decided they would like to do an AGU session next year in South America. So if anybody's interested, please see me. Monica Morrison and I will be convening that session. And we will be sending out invitations probably in May or so, May, June. And we've been doing workshops on convective permitting. We've had a couple in Japan. We had one in Zurich. We had a couple at NCAR. And the next one we're thinking about having is in South America. I'm talking to one of our colleagues in Buenos Aires, and they're thinking of hosting it there in 2022. Hopefully the pandemic is over by then. So we have a history of looking at the continental US with the convective permitting modeling, which is less than 4 kilometers delta X with the WRF model. And we decided to do the similar approach over South America. One of the goals is to take our best configuration for the continental US and apply it to South America. And hopefully, if things, cross our fingers, if everything works similar in South America, we should be able to get similar success there with the same configuration. And so far, so good. It's looking good. We've done 2 months and we've done a 1-year simulation. And so far, that hypothesis is holding. And we are working with Rich Neal and Julio Bachmeister and Chris Cruzy and others to compare your variable resolution CESM to some of these simulations. So we're sharing exactly the configurations. We've talked to Patrick Callahan about our vertical levels, et cetera, and they've been attending our meetings. And so we hope to be able to compare and contrast the 2 models. There are not as many observations in South America as we have in the US. the most notable being the lack of radar observation. So we have to rely a little bit more on satellite data. So the first request we had was for 3 years to the CISL NSC group. And then the second request is coming up in March next month. And we are going to request 20-year current and future climate simulations. And Rich Neal is also requesting some time to do some variable resolution simulations in collaboration with our simulation. So they will be coordinated requests. And we just talked about that today. We started out in September 9th, 2019, shortly after we got started, with a 3-year request to CISL that was granted to Francino Dominguez, who's a professor at University of Illinois, originally from Columbia, led that effort. And we have now done some of those years, and it looks pretty good. And so we're now putting that together for a 20-year current and 20-year future simulation. And that's what we're working. We worked on that this morning, and we're going to continue working on that request over the next few meetings, with the goal of getting it submitted to the large university large allocation request on March 22nd. Francina has a NSF grant related to South America. So enough words. I'm going to show you some graphics now. This is a graphic of the South America domain compared to what we've done in the continental US. And you can see South America is a pretty big continent, and it's essentially, it's very similar in size to our second domain here, which we call CONUS number 2. And that, by the way, CONUS number 2 is driven by CESM. So for this particular configuration, our test configuration, we went from June 18th to May 2019. We forced it on the boundaries with ERA 5. And one of the things that we had done in our continental US simulations is used spectral nudging. So essentially the large wave numbers were maintained, were calculated, and the flow was nudged to those large wave numbers. So the idea was, the extratropical cyclones coming in on the West Coast would maintain their storm tracks. In South America, we tested both nudged and non-nudged, and it looks like the nudging is not as important for, especially down south. It gets pretty narrow where the extratropical cyclones come across. Near the equator is up here, near Colombia. The tropical convection doesn't seem to need the spectral nudging. And Julio talked us out of it and saying we need to allow things to freely evolve if we're going to look at this in the future climate as well. So we're running it without nudging at the moment. And we're running similar physics as we ran in the continental US. So I'll show you some results now. As I mentioned, we don't have as much radar data, so we use the iMerge satellite data. We use, on the left, we have brightness temperature from GridSat, and precipitation from the iMerge satellite sensor. And I want to just mention here that this is work by Andreas Prine. This is a team effort. Shanghai Liu has been doing a lot of the modeling, and Kyoko Ikeda has been involved with the archival and variable and QC. And Andreas Prine has been doing a lot of the analysis. And there's a team of about 10 other folks that I don't have time to mention, but just make sure that you don't think I did all of this. This is all material that has been generated by our team. So you can see on the left the observations, and on the right the WRF model. And you can see that given the boundary condition forcing on the outer gray, the model does a really quite a good job capturing the precipitation and cloud field. This is the 6 days in November. You can see in the Amazon, we generate some large cloud systems that we call MCSs. I'll talk about that later. And here's a MCS that was well observed during the Relampico field campaign right here. And you can see it's captured both in the model and then obviously in the satellite ops. So what Andreas Prine did is he tracked those MCSs, and these are the tracks from the satellite in the black and the model in the red. And you can see, as you saw in that video loop, the model is doing quite a good job capturing those MCSs, especially here in Argentina. That was, I believe, the one in November. And you can see the tracks tend to follow each other. So I'm very, very happy with this. And this is a detailed view of the Relámpago MCS right here. You can see how the model and the observations compare. And so something else that Andreas did is he counted the number of storms in the Amazon basin and in the La Plata basin. La Plata is down here in Argentina. Amazon is up here in Brazil. And the red is the model and the black are the observations. And you can see the model is doing pretty darn good job capturing the number of these storms per month. And they tend to be a little bit smaller in the Amazon basin than in the La Plata. The La Plata is where you get some of the biggest hail in the world. But you can see the frequency of storms is captured quite well in the WRF simulation. So I don't want to take up a lot of time, but I can show you lots more graphics. But the storm size and precipitation rate, et cetera, all looks quite good. So in general, the 4-kilometer WRF captures the diurnal cycle of precipitation amount, frequency, intensity across South America. That's been a theme of the water system for many, many years. And also I showed you the frequency and annual cycle of organized convective storms, also well captured. And according to Andreas, he thinks that the model performance is better than our initial simulations over North America. And as I mentioned, we kept the model physics basically the same. So that's really good news. One of the nice things about WRF is that we can do these nested domains called NDOWN using this software package called NDOWN. And a number of folks want to look at the Amazon basin. Francina Dominguez wants to look up here in Colombia. Others want to look down in Argentina and look at, so these are, after you run the 4-kilometer run for 20 years or so, then we can do 1-kilometer nests over these particular regions to get even finer. And this was the agenda that we had at the water cycle retreat. The second day, the morning was devoted to South America. And we had a mix of talks from Herman Poveda, who is a Colombian professor of hydrology, well-known South American water cycle scientist. He gave a great keynote. By the way, all of these talks are recorded and available. So if anybody's interested, let me know. And Francina gave a wonderful talk about water vapor recycling over the Amazon. So next steps, as I mentioned, we're working on those 3-year simulations. We completed 1 year. I showed you some results. We're working on the NSC university request for 20 years. That's due in March. And we're working with Julio and Rich Neal and Patrick and others to intercompare the CESM variable resolution simulations. And we hope to move towards CEMA in the future as part of our water system retreat. Andrew gave a nice talk on CEMA the first afternoon. And I think it's going to take a while, but we're hoping to migrate from WRF to CEMA and do the global simulations in the next 2 to 3 to 4 years. But in the meantime, we can help with the CEMA effort by looking at some of these processes in different continents. And right now we're focused on South America. So that's all I had. And I'll stop here and take any questions. Hope I didn't go too long.
Thanks, Roy. I don't see chat questions, but I open it up. If you have a question, please unmute yourself. I actually had a quick question concerning the I guess, a technique. Did you restart the WAF simulation at times, or was it a free running simulation that was just started once?
A free running simulation. Once in a while, the model crashes and you have to restart it. We save restart files every 2 weeks, so in case we have to restart it. And for the 1 kilometer nest that I showed you, we do use the restart files.
But are you using? You're not updating initial conditions.
No, we're not updating it.
Yeah.
No,
Okay.
it's just constantly being, and that's a really good question. I get this question all the time. And initially we weren't sure if this would work or not, but proof is in the pudding. We tried it and it does seem to work quite well over the continental US, and it clearly works fairly well in South America as well.
Because often models at these convective scales break down after 2 or 3 days and don't really match the observations any longer. So I was surprised to see a 6-day simulation.
ERA 5 every I think it's 3 hourly. ERA interim was 6 hourly. So we constantly update the boundary conditions.
The boundary conditions, right.
Take care of it.
Yeah.
And you mentioned there's no internal nudging going on, right?
No nudging, Julio. That is your recommendation.
I was just hoping you could just give a brief description of how you do the climate change simulations in these frameworks.
Oh, sure. We are planning to do some climate change simulations. Let me go back to my presentation and I'll show some of that. Now, the challenge with doing such high resolution is that we really can't afford to do a lot of ensembles. In fact, we can't do any ensembles. So we have to do one climate simulation. So we started in the continental US, and so on this smaller domain over continental US, we use something called what Japanese call the pseudo global warming approach. This was invented by Christoph Scharr at ETH back in Europe in 1997. And essentially we take the average of the climate model, temperature and humidity, and add it to the boundary conditions, the ERA 5 or the ERA interim boundary conditions. And then we rerun the future with, say, RCP8 forcing and the average temperature and humidity added. So what we don't do is we don't change the dynamics, but we can answer a question, something along the lines of what would the current climate look like in a future warmer and moister world?
When you say don't change the dynamics,
change the dynamics.
You mean but in the case with no spectral nudging, the dynamics would be free to do whatever they want in the.
That's right. With no spectral nudging, the dynamics, like in South America, we don't have any spectral nudging, so the storms can evolve however they want to. So, and this is a little bit scary for me because it works so well with spectral nudging up above. The big large domain is called CONUS 2, and with that one, with the historical, we forced the boundary with the CESM global runs for the current and CESM future, but we were only one ensemble member. So this is clearly something that we'd like to do, run multiple ensembles. So hopefully exascale and GPUs will come to our rescue eventually. So in South America, we're currently planning to do the pseudo global warming on the 20-year run force with the reanalysis, and then add the temperature and humidity perturbation by averaging the 19 CMIP 5 or 4, no, not 5, 6, I think it's 6 now, models, and using that to the monthly mean and adding that to the boundary conditions, and then using that for the climate forcing. Obviously, we're not where we want to be there with that yet, but that's just a reality of the amount of computer times it takes to run at 4 kilometers. And the data storage is huge. So one of the biggest challenges we have is finding enough space to save all the data.
So we are now in the middle of the discussion period. I suggest that we maybe use another 20 minutes or so, maybe end by 4 p.m. Mountain Time. I want to open it up. Maybe Roy, can you stop sharing? Yeah, thank you. I want to open it up, of course, to all the speakers and all the themes that we heard about. And this was the session about potential future directions we take in Earth system models. We heard from SCREAM, from Peter Caldwell, and also the CAM or WAF-related model simulations. So this is a free-flowing discussion. So please either raise your hand or speak up if you want to contribute some thoughts. Maybe starting with the question for Peter. This was a pretty impressive new development that you do at DOE. Can you maybe comment a little bit on timelines, and is E3SM phasing out? Maybe give us a little bit of an idea of what the timeline is.
So we started this effort 2.5 years ago to get to the point that I discussed today. So I don't think it would have taken us that long to just be able to run the Fortran version of the at 3 kilometers, although there's all sorts of pitfalls along the way in terms of, you're running on, I think we run on like 1,536 nodes of Cori, which is a lot. And so that causes things to crash and you have to fix bugs there and so on that I think that you'll probably face on the CESM side when you do this as well. Yeah, we spent a lot of time porting the code to C++, designing a new coupler and things like that in terms of intra-atmosphere coupler. We're hoping to be able to start our C++ simulations this next summer. So we're just in the final stages of coupling the different processes together. And so Xiaocheng pointed out, I said that, that this is going to be the V4 version of E3SM. And he pointed out that there's some ambiguity of that still, whether there's still going to be a parallel track of the kind of the version that extends from CESM when E3SM branched off. So that's a little bit unclear. Does that answer the question to you?
Yeah. Anybody on this topic, or also we heard about GPU performance as well with this effort, or Gunther?
I had a question for Gunther. I was wondering if his subcolumn approach allows, any memory from any memory across time in the subcolumns, or does a GPU implementation require that everything's sort of invented from, available information at each time step?
Gunther, are you still on?
I don't think he is.
Oh, okay. Oh,
I don't
all right.
see him in the participants.
I think, yes, we lost
So can I just jump in and say, how does the SP-CAM work? Doesn't that essentially puts the columns and runs the super parameterization on the node, but then goes back to the data later? That's my understanding, is the data can stay on the node, and then you do the kind of larger scale off the node, and you come back and you restart the state from the same position. That was my understanding.
So SP-CAM does have memory of its.
Yeah, it doesn't forget what it was doing at the highest resolution, essentially. Yeah.
So okay, so you're kind of saying that would be you could use the same model would apply for these subcolumns.
Yeah, it would make sense to retain that, I guess.
Yeah, is SP-CAM GPUized?
I'm sure someone's wasted their time doing it. No, I'm sure someone has done a good job doing that.
Maybe Peter knows that, actually.
Yeah, E3SM has a huge effort to run MMF on GPUs.
Okay.
It works pretty well.
But Julio, I think the answer to your question on whether it operates in a similar way to SPCAM is no, because the PDFs are recalculated at every time step.
Right, but there's no technical hurdle in the GPU architecture to having the GPUs remember where they were. That if you wanted to have a PDF that kind of used its previous state as a part of the recipe, you could. Do you think that's true?
Oh, I have no idea.
Okay.
I think that's true because the power of SPCAM is that you retain those states which are organized, and then you can the momentum transport, for example, is it's important that you retain that organized state from time step to time step.
I had another more general question, also about GPUs in the sense that, so it sounds like, if I heard correctly, the next NCAR machine is going to be 20% GPUs, and there's certainly an effort to have CAM be kind of GPUized. Does anyone have a vision for what this is going to mean in terms of general users, like everyone in this audience? So is the code going to be harder to read because it's going to have all sorts of like OpenMP statements in the middle of it and so on, or
That's even an open question. Maybe some of the NCAR folks can tell us what the GPU technique is. Is it OpenACC, OpenMP, or CUDA, or any of these?
I'm going to plead complete ignorance on this issue.
Rich, do you know?
I do believe it's ACC, but Andrew knows if he's avoiding. They've just announced it like last week or 2 weeks ago. So in terms of the architecture,
I'm pretty sure it's ACC directive based. That's what I understand. And I think the way it's going to work is there's 20% of the machines available for that for people who can use it. So you can totally ignore GPUs if you want on the machine, but there'll be a pile of them available. And if they are used more, there is the option of expanding the machine in the GPU direction. So they have architected it so if GPUs are useful and they're subscribed well, they may expand the machine in that direction. But they would not expand the machine for CPUs, as I understand it.
So NCAR takes the lead to provide the GPU support in CSM?
I wouldn't say that that's coherent yet. I would say that we are committed through Dave Randall's Earthworks project, which is part of SEMA, to move at least one configuration of CESM onto GPUs. And so that's an effort that's moving forward. We're exploring that with CISL right now in various different pieces, and that's going to move forward over the next couple of years, but it's a 5-year project. So don't expect to download a CESM release that has GPU capability anytime soon would be the overall message. We are moving in that direction to the extent we can get help doing that and leverage that, we are doing that. So there are ongoing, CISL is doing ACC trainings now. That's starting up. I've suggested that we need one for scientists to be able to read the code or hack the code. And I think we're going to be moving more in the direction and starting to convert the code as we go forward. So we've already well along on the microphysics. Obviously, UWM has done it already. We're doing it also with CISL, so we'll have to collaborate on that. And then it's a question, I think there's a version of RRTMG that is on RRTMGP. I think there's a GPU version. So that's the radiation code. MPAS is a GPU version as a dynamical core. So we're planning on using that or having that available. So we are getting to the point where there's more and more GPU codes for different pieces of CAM, and it becomes pulling off a small number of physics parameterizations that have to be moved onto the GPUs. So I think we're actually going to get there in a few years, is the bottom line.
And maybe related question, pretty open-ended. Does NCAR have a machine learning strategy?
I don't know if it's a single strategy, no, but we have a bunch of different machine learning efforts, some of them in CAM, as you were mentioning. And there's not an overarching strategy. However, there is a machine learning group inside of CISL. I think the strategy is being run through there with in the technology development division. Obviously, the tools are available to do that on the machines, and they've got, part of the reason they're getting, they have GPUs is to enable the efficiency of some of the machine learning for data analysis and model development. So
yeah, I just noticed there's a big push at ECMWF to really advance this capability for all kinds of reasons, not just within the model IFS, but also for corrections of predictions via machine learning, downscaling. There are all these application areas. So that could also be something that NCAR wants to look at.
Yeah, I would say we don't have a coherent strategy because there's like many things in CESM and NCAR. There's many, there's 1,000 flowers blooming from below, and there's lots of things bubbling up, and we're already pulling that. I mean, I didn't talk about it here. I've talked about it in the past, but we have as I mentioned earlier, we have with CISL architected and implemented basically methods to call neural network to take TensorFlow output, turn it into weights, load that through Fortran into CESM and call it. And we've been pretty effective at doing that with inside of the physics. So I think those things we can make available to people, those tools to actually do work inside of CAM with machine learning and neural networks. We may actually roll one out in the microphysics. We've gotten some really nice results so far. I think we may wait a generation till we get some more physics constraints in it, but we're pacing that. So I think we're kind of watching a bunch of efforts, and I know, Christian, you have different efforts. I know there's big efforts with different science technology effort. There's a big effort that just got funded on the CICE side to do machine learning in the CICE model. So I think it is very active and bubbling up, and we'll probably see a little more strategic discussion of that, would be my guess.
Maybe a good topic for our summer meeting or next year even.
Yeah, as a cross working group thing for this summer, that would be you're right, that would be a great topic.
Yeah.
Good idea.
So Roy, we had also a few more questions for you in terms of your setups, I guess related to vertical resolution. This maybe relates also to earlier discussions that you had on Monday. If you're still online, you maybe can answer this question. What's your setup for your high resolution simulations? Because it does matter at these very high horizontal resolutions, you do need a high vertical resolution as well.
Yes, we have about, I think we have 50 levels, starting small, relatively small delta Z near the surface, and then expanding upwards. So that's the vertical levels.
Is the model top, where is that located?
We had some discussion about model top in South America because the gravity waves go so high off of the Andes. So I think did we end up at 50 millibars, Julio? I think that was the last.
Yeah, I thought WRF was still going to top out around 30 kilometers.
Yeah. Okay.
And our CAM equivalent run will go all the way to 45, but
I think we decided to put in a sponge layer at the top to prevent some of the reflections of the gravity waves coming back.
And that's typical a deep sponge. Huh?
I think we were talking, it takes, we have a trade-off a little bit about computer time and the sponge, the number of levels. So we decided to, I think we had 10 kilometer sponge layer. I think we went down to 5 kilometers currently, and it seems to work fairly well. One of the things that we have done lots of work on is test runs, and we do 2-month test runs, and we've done nudging, no nudging, sponge, the difference in the sponge layers and the gravity waves, the depth of the cloud top. And I have a slide that has some of the details. I don't have it in front of me at the moment, but we've done many sensitivity studies to try to make sure that our configuration is reasonable and produces reasonable results. And that's been really great to have a variety of scientists involved who can speak to various phenomena like the Andes low-level jet and the gravity waves, MCSs, et cetera.
Chris Cruz might have some more comments on the vertical grid.
Yeah, Chris has been great with the gravity waves studies. Do you have any comments, Chris? Are you still there?
Sorry, yeah. Can you hear me now? I'm having trouble unmuting.
Yeah, we can hear you.
Well, my comment was that I recommended a 10-kilometer deep sponge. I think at the time you had a top at 25 kilometers, and I suggested just upping it to 30 and having a 10-kilometer deep sponge. But I don't know what you guys decided in the end. So.
The levels that Shanghai forwarded to me top out at 10 millibars at 30 kilometers.
Okay, 10 millibars. Okay, so we did listen to Chris. Okay, there's
61 levels.
61 levels. Okay. We started at 50 in our CONUS runs, and so we increased it a little bit for the goal is to try to keep the same number of levels in your runs, Patrick, as the ones that we have in the WRF model.
Yeah, and I think we're going to probably go a little bit higher to 40 because that's kind of like where our top is, 40 kilometers. So we're going to, kind of stretch it out a little bit higher for our runs.
Sounds good.
I had a question for Adam Harrington about the South America simulations, kind of related to what you've been doing with the High Mountain Asia project. So these are going to be down to 3 kilometers in CSM. I know the non-hydrostatic. I mean, we're obviously pushing the limits of CAM-SC quite a bit, but the topography at least will be resolved down to 3 kilometers with smoothing, of course. But is there a possibility of at some point incorporating the mountain, the glacier models that you guys are using in the High Mountain Asia grid?
Yes. So I think that's, we went through the procedure of producing a new glacier region, and it wasn't that difficult to do. The CLM name list, some of the relevant ones that control the glacier regions are vectors, so that the first entry would be for the Antarctic region, the second entry would be for Greenland region, and so and so. So you just sort of add another glacier region by just increasing that array by 1.
Okay.
So yeah, we can help you with that if it gets to it. What we did is we were able to we ran the CLM model, and we told it it's a glacier region, so that in the coupler, it runs CLM at a bunch of elevation classes. We have not taken the extra step to actually map those elevation classes to a high resolution ice sheet grid. And so that's gonna take a little more work, but it's doable for sure.
Okay.
And there's a potential to do Leo Van Kampenhout has an offline Python script that you just provide it the coupler output with the elevation classes and some sort of digital elevation model you want to map them to. And so you could compute the surface mass balance in that downscaled approach with an offline script, provided you save the coupler output.
Can I ask you, which model are you talking about to run this in? Julia, is it WRF you're talking about?
Right now we're talking about CESM.
Oh, CESM, okay.
You talked about uncertainty quantification and the perturbed parameter ensemble. Can you maybe shed some more light on it? Was this done with earlier versions of the model, CAM-5, and what's kind of the history behind it? What can we learn from it?
We haven't done anything, so we so it has not been done with CAM-5. And if Andrew Gettleman is here, maybe he can answer.
Yeah, actually, versions of it have been done. PNNL did a couple of really nice studies, first with SCAM and then with CAM, looking at parameter perturbations in a sort of slightly less formalized framework, but similar methods of multiple sampling and things like that. That actually proved very valuable. And that was actually done for CAM6 prototypes. It was done for CAM Club, for example. And so that was actually traditional. That was something we used quite a bit for actually tuning up CAM6 and looking at sensitivities of different club parameters. The intent is to do that again with the full CAM6 physics suite, and to basically use a methodology that is both repeatable and extensible and available to the community. So the nice part about this is we can save the parameter sets as netcdf files, and you can repeat them with a different comp set.
Can you remind us, was that coupled or uncoupled?
Those are all uncoupled. So we're also focusing on the atmosphere, just looking at coupled, uncoupled. But you can do it coupled if you really want to. So.
Okay, so 6 o'clock, last call for discussion items. 6 o'clock my time.
I guess it's the
Call
end of
it
a long day.
Yeah, long day. Yeah, 6 o'clock p.m. here, East Coast.
Right.
So thanks everybody for participating in the afternoon session today. We reconvene. Julio, help me.
Yes, tomorrow the tropospheric chemistry and music session will start at 9.
Mountain time, right?
9 Mountain time, exactly. And we'll go till 11:30. And then at 1 Mountain time, there will be a wrap-up discussion with breakouts. So I hope people will be able